In 1938, a German archaeologist named Wilhelm König was examining a collection of artifacts in the basement of the National Museum of Iraq in Baghdad when he noticed something that did not belong. Among the pottery, the tools, and the ornaments that had been recovered from archaeological sites across Mesopotamia, there was a small clay jar, roughly 15 centimeters tall and about 8 centimeters in diameter, that contained an arrangement of components that made no sense in the context of an ancient archaeological collection. Inside the jar was a copper cylinder, approximately 9 centimeters long, sealed at the bottom with a copper disc and capped at the top with a plug of asphalt. Inside the copper cylinder was an iron rod separated from the copper by the asphalt plug and suspended in the center of the cylinder without touching the copper walls. The iron rod showed signs of corrosion, as if it had been immersed in an acidic liquid. König recognized what he was looking at. He had studied electrical engineering before turning to archaeology, and the arrangement of components inside the clay jar was, to his trained eye, unmistakable. A copper cylinder, an iron rod, an electrolyte, the acidic liquid that had corroded the iron. These are the three components of a galvanic cell, the simplest type of electrochemical battery, a device that converts chemical energy into electrical energy through the reaction between two different metals in an acidic or alkaline solution. The artifact König was examining appeared to be a battery, an electrical device, produced in ancient Mesopotamia approximately 2,000 years ago. The jar was not unique. Several similar artifacts had been found at the same site, a Parthian-era settlement near the modern village of Qhapaq, southeast of Baghdad. The artifacts were dated to the Parthian period, roughly the 1st century before the Common Era to the 3rd century of the Common Era, a period when Mesopotamia was ruled by the Parthian Empire, a powerful state that controlled much of the territory between the Roman Empire and the Indian subcontinent. The artifacts were small, unassuming, easily overlooked among the thousands of other objects that had been recovered from the site. But if König's interpretation was correct, they were among the most extraordinary objects ever recovered from the ancient world. If the Baghdad battery is what it appears to be, then the ancient inhabitants of Mesopotamia possessed a knowledge of electricity that predates the modern discovery of electrical phenomena by approximately 1,800 years. Alessandro Volta, who is credited with the invention of the first true battery, the voltaic pile, presented his invention to the Royal Society of London in 1800. If the Baghdad battery is a galvanic cell, the people who made it understood and exploited the same electrochemical principle that Volta discovered nearly 2 millennia before Volta was born. By the end of tonight, you are going to understand what the Baghdad battery is, what the evidence for and against its interpretation as an electrical device looks like, what experiments have been conducted to test the battery hypothesis, and what alternative explanations have been proposed for the artifact's function. You are going to learn about the specific archaeological context in which the artifacts were found, the specific scientific analyses that have been conducted on them, and the specific debates that continue to divide the scholarly community. And you are going to confront a question that touches on the very nature of technological progress. Is it possible that the ancient world discovered electricity, used it for practical purposes, and then lost the knowledge, leaving behind only a handful of enigmatic clay jars as evidence of a capability that the modern world would not rediscover for nearly 2,000 years? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Baghdad battery is one of the most debated artifacts in the history of archaeology. It has been cited as evidence of ancient electrical technology by proponents of alternative history. It has been dismissed as a misidentified storage vessel by skeptics. It has been tested by experimenters who have confirmed that it can, in fact, produce a small electrical current, and it has been studied by scholars who remain divided after nearly 90 years of debate about what it was used for, and what it tells us about the technological capabilities of the ancient world. The debate is not settled. The evidence is ambiguous. and the questions that the Baghdad battery raises are as provocative today as they were when Wilhelm Koenig first noticed the strange arrangement of copper, iron, and asphalt in the basement of the Baghdad Museum. Now, let us begin. The implications of Koenig's discovery have reverberated through nearly a century of scholarship, generating a debate that has drawn in archaeologists, chemists, electrical engineers, ancient historians, and the general public in equal measure. The Baghdad battery occupies a unique position in the history of ancient technology. It is the only artifact from the ancient world that has been seriously proposed as an electrical device, the only physical object that suggests, however tentatively, that the ancient world may have possessed a knowledge of electrochemistry that was not formally discovered by modern science until the very end of the 18th century. The object is small enough to hold in one hand. It is made of the most ordinary materials: clay, copper, iron, bitumen, materials that were available to any craftsman in the ancient Near East. It contains no exotic ingredients, no rare metals, no materials that would have been difficult to obtain or expensive to purchase. And yet, if the battery hypothesis is correct, this small, ordinary object represents one of the most extraordinary technological achievements in the history of the ancient world. The deliberate exploitation of an electrochemical phenomenon that the modern world would not formally identify for another 18 centuries. To understand the Baghdad battery, we must first understand the civilization that produced it and the technological context in which it was created. Mesopotamia, the region between the Tigris and the Euphrates rivers in modern Iraq, was one of the cradles of human civilization, and the people who lived there over the course of several millennia produced some of the most important technological innovations in human history. Writing, mathematics, astronomy, agriculture, urbanization, law, and dozens of other fundamental innovations were either invented or significantly developed in Mesopotamia, and the region's contributions to human civilization are so extensive that it is difficult to overstate their importance. The specific period in which the Baghdad battery was produced, the Parthian period, from roughly the 3rd century before the Common Era to the 3rd century of the Common Era, was a time of considerable cultural and technological sophistication in Mesopotamia. The Parthian Empire, which was founded by the Arsacid dynasty, and which, at its height, controlled territory stretching from the Euphrates to the Indus, was one of the great powers of the ancient world, rivaling the Roman Empire in wealth, in military power, and in cultural achievement. The Parthian period in Mesopotamia was characterized by a blending of Greek, Persian, and Mesopotamian cultural traditions that produced a cosmopolitan civilization with access to a wide range of technologies and intellectual traditions. The metallurgical traditions of ancient Mesopotamia provide essential context for understanding the Baghdad battery. The people of Mesopotamia were among the earliest and most skilled metalworkers in the ancient world, and they had been working with copper, bronze, gold, silver, iron, and other metals for thousands of years before the Parthian period. The copper cylinder and the iron rod that are the key components of the Baghdad battery are products of a metallurgical tradition that was highly developed and that had accumulated millennia of experience in the properties and the behavior of metals. The production of copper objects, which required the smelting of copper ore, the casting or hammering of the molten or heated metal, and the finishing of the surface, was a well-established industry in Mesopotamia from the 4th millennium before the Common Era. The production of iron objects, which required higher temperatures and more sophisticated techniques than copper working, was established in the region by the early 1st millennium before the Common Era. The fabrication of the copper cylinder and the iron rod that are found in the Baghdad battery would have been well within the capabilities of a Parthian-era metalworker, and the specific techniques required, cutting and rolling copper sheet, drawing or forging an iron rod, are basic metalworking operations that were standard in the ancient world. The use of asphalt, or bitumen, which is the material used to seal the top of the copper cylinder, and to insulate the iron rod from the copper, was another well-established technology in Mesopotamia. The region is rich in natural deposits of bitumen, which seeps to the surface from underground petroleum deposits, and the use of bitumen as a seasonant, a waterproofing agent, and an adhesive has been documented in Mesopotamia for thousands of years. The bitumen deposits of the Hit region in central Iraq, which have been known and exploited since at least the 3rd millennium before the Common Era, provided a ready supply of the material that was used in the Baghdad battery and in countless other applications across the ancient Mesopotamian world. The electrochemistry that would explain the Baghdad battery's operation is, in principle, simple. A galvanic cell produces electrical energy through the oxidation of one metal, the anode, and the reduction of another metal, the cathode. In the presence of an electrolyte, a liquid that conducts electricity through the movement of ions. In the Baghdad battery, the iron rod would serve as the anode, the copper cylinder would serve as the cathode, and the acidic liquid that was contained in the jar would serve as the electrolyte. The oxidation of the iron, which releases electrons, and the reduction of the copper, which absorbs electrons, would create a flow of electrons from the iron to the copper through any external circuit that connected the two metals, producing an electrical current. The voltage that a single Baghdad battery would produce depends on the specific metals used and the specific electrolyte, but experiments with replicas have shown that a single cell can produce a voltage of approximately 1 to 2 volts with a very small current of a few milliamperes. This is a tiny amount of electrical energy by modern standards, roughly comparable to the output of a small hearing aid battery, but it is enough to produce measurable electrical effects and enough to have practical applications in certain specific contexts, as we shall discuss. The question of what electrolyte the Pantheon-era users of the Baghdad battery might have employed has been the subject of considerable speculation. Several acidic liquids that were available in the ancient world could have served as electrolytes, including vinegar, which is a dilute solution of acetic acid, wine, which contains tartaric acid and other organic acids, citrus juice, which contains citric acid, and grape juice, which contains a mixture of organic acids. All of these liquids are capable of conducting electricity through the movement of ions, and all of them would support the electrochemical reaction between iron and copper that would produce an electrical current. The broader context of ancient knowledge about electricity and related phenomena is important for evaluating the Baghdad battery hypothesis. The ancient world was not entirely ignorant of electrical phenomena, though the understanding of these phenomena was fragmentary and unsystematic. The ancient Greeks were familiar with static electricity, which could be produced by rubbing amber against cloth or fur, and the Greek word for amber, electron, is the root of the modern word electricity. The ancient writers described the ability of amber to attract small objects after being rubbed, a phenomenon that is now understood as the result of the accumulation of static electrical charge on the surface of the amber. The electric fish of the Mediterranean, including the torpedo ray, which produces electric shocks of up to 200 volts, were known to the ancient Greeks and Romans, who used them for medicinal purposes, applying the fish to the bodies of patients who suffered from headaches, gout, and other ailments. The use of electric fish for medical purposes demonstrates that the ancient world was aware of the physiological effects of electricity, even though the nature of the electrical charge produced by the fish was not understood. The ancient understanding of electrolysis, the process by which an electrical current causes a chemical reaction, is not documented in any surviving ancient text, but the possibility that the ancients observed the effects of electrolysis without understanding the process cannot be ruled out. If the Baghdad battery was used to produce an electrical current, the current could have been used for electrolysis, the deposition of metals from solution onto a surface, a process that is now known as electroplating. The electroplating hypothesis, which proposes that the Baghdad battery was used to deposit a thin layer of gold or silver onto the surface of objects such as jewelry, statuettes, or ornaments, is one of the most widely discussed applications of the battery, and the one that has received the most attention from researchers. The tradition of metalworking in the ancient Near East provides important context for the electroplating hypothesis. The ancient metalworkers of Mesopotamia, Egypt, and the broader Near East were highly skilled in the production of gold and silver objects, and they had developed a variety of techniques for applying thin layers of precious metal to the surfaces of less valuable objects. These techniques included fire gilding, in which gold was dissolved in mercury and the amalgam was applied to the object's surface and heated to drive off the mercury, leaving a thin gold coating; leaf gilding, in which thin sheets of gold leaf were applied to the surface using an adhesive; and depletion gilding, in which a silver-gold alloy surface was treated with acid to dissolve the silver, leaving a thin layer of pure gold on the surface. The existence of these alternative gilding and plating techniques raises an important question for the electroplating hypothesis. If the ancient metalworkers already possessed effective techniques for applying precious metal coatings to objects, why would they have needed to develop an electrical technique for the same purpose? The alternative gilding techniques were well established, widely practiced, and effective, and the additional cost and complexity of an electrical technique would have needed to be justified by some advantage that the electrical technique provided over the existing methods. The identification of such an advantage is one of the challenges that the electroplating hypothesis must address. The archaeological context in which the Baghdad battery was found is also important for evaluating the various hypotheses about its function. The artifacts were recovered from a Parthian-era settlement near Qujut Rabu, a site that has not been extensively excavated and whose overall character and function are not well understood. The specific context in which the battery-like artifacts were found within the site, whether they were found in a workshop, in a temple, in a domestic dwelling, or in some other type of structure, is not clearly documented in the surviving excavation records, and the loss of this contextual information has hindered the interpretation of the artifacts. The damage to the archaeological record caused by the two Gulf Wars and the subsequent looting of the National Museum of Iraq in 2003 has added another layer of difficulty to the study of the Baghdad battery. Some of the original artifacts were damaged or lost during the looting of the museum, and the excavation records and the associated documentation have been partially destroyed or dispersed. The loss of the original artifacts and the associated documentation means that some of the questions about the Baghdad battery may never be answered because the physical evidence that would have been needed to address them is no longer available. The intellectual traditions of the ancient Near East provide additional context for evaluating the possibility that the Mesopotamians might have discovered the electrochemical phenomenon. The civilizations of Mesopotamia were among the most intellectually sophisticated in the ancient world, and their contributions to mathematics, astronomy, medicine, and law demonstrate a capacity for systematic observation, for the recording and the transmission of knowledge, and for the practical application of intellectual discoveries that is consistent with the hypothesis of an electrochemical discovery. The Babylonian mathematical tradition, which developed over a period of more than 2,000 years, and which produced a number system, a system of measurement, and a body of mathematical knowledge that influenced the subsequent development of mathematics in the Greek, the Indian, and the Islamic worlds, demonstrates the intellectual sophistication of the Mesopotamian civilization. The Babylonian astronomers, who compiled centuries of systematic observations of the celestial bodies, and who developed mathematical models for predicting the movements of the sun, the moon, and the planets, demonstrated a capacity for sustained, systematic observation that would have been relevant to the discovery and the development of an electrochemical technology. The medical traditions of ancient Mesopotamia are particularly relevant to the Baghdad battery debate because one of the proposed uses of the battery, the production of an electrical sensation for therapeutic or ritual purposes, is consistent with the known medical practices of the ancient Near East. The Mesopotamian medical tradition, which is documented in thousands of cuneiform tablets, included a wide range of therapeutic practices, including the use of herbal remedies, surgical procedures, and various physical interventions that were designed to alleviate illness and to restore health. The use of an electrical sensation, whether produced by a Baghdad battery or by a natural source such as an electric fish, would have been consistent with the empirical trial and error approach to medicine that characterized the Mesopotamian tradition. The alchemical traditions of the ancient Near East, which included the practice of metallurgy, the production of dyes, the formulation of medicines, and the transformation of various substances through chemical processes, provide another context in which the discovery of the electrochemical phenomenon might have occurred. The ancient metalworkers and alchemists of the Near East routinely worked with metals, acids, and other chemical substances, and the accidental discovery of the electrochemical phenomenon through the immersion of dissimilar metals in an acidic solution is a plausible outcome of the kind of experimentation that was routine in the ancient alchemical tradition. The trade networks of the Parthian Empire, which connected the eastern and the western halves of the ancient world, facilitated the exchange of goods, ideas, and technologies across vast distances. The Parthian Empire was a major node in the Silk Road trade network, and the goods that passed through Parthian territory included not only physical commodities but also intellectual products, including scientific and technical knowledge that was exchanged between the Greek, the Persian, the Indian, and the Chinese intellectual traditions. The possibility that knowledge of the electrochemical phenomenon, if it was discovered in Mesopotamia, could have been transmitted to other parts of the ancient world through the Parthian trade networks is one that has been considered by researchers, though no evidence of such transmission has been identified. The specific funerary and religious practices of the Parthian period are also relevant to the interpretation of the Baghdad Battery. The Parthians practiced a variety of religious traditions, including Zoroastrianism, which emphasized the opposition between light and darkness, and which incorporated fire worship, and various ritual practices that involved the manipulation of physical phenomena. The possibility that the Baghdad Battery was used in a Zoroastrian or other religious context, perhaps for the production of a spark or a light effect that was interpreted as a manifestation of divine power, is one that has been explored by researchers who specialize in the religious history of the Parthian period. The history of the study of the Baghdad Battery itself provides an instructive case study in the sociology of archaeological interpretation. Koenig's original publication of his identification of the artifacts as batteries, which appeared in a German-language journal in 1940, was received with a mixture of interest and skepticism by the scholarly community. The interest was generated by the dramatic implications of the identification, which, if correct, would have overturned the established understanding of the history of electrical technology. The skepticism was generated by the weakness of the evidence, which was limited to the physical form of the artifacts, and which lacked the contextual support that would have been needed to confirm the identification. The reception of the battery hypothesis in the decades following Koenig's publication illustrates the way in which extraordinary claims are processed by the scholarly community. The hypothesis was taken seriously by some researchers who conducted experiments with replicas and who explored the possible applications of the device, while it was dismissed by others who pointed to the weakness of the contextual evidence and to the availability of alternative explanations. The debate between the proponents and the critics of the battery hypothesis has continued for decades, and it has been conducted in scientific journals, in popular books, in television documentaries, and on the internet, with each new contribution adding to the body of evidence and argument, but without producing a definitive resolution. The popularization of the Baghdad Battery by television programs, popular science books, and alternative history publications has had a mixed effect on the scholarly debate. On the positive side, the popularization has generated public interest in the artifact and has stimulated research by bringing the artifact to the attention of scientists and engineers who might not otherwise have been aware of it. On the negative side, the popularization has sometimes distorted the evidence, presenting the battery hypothesis as though it were established fact rather than an unproven hypothesis, and ignoring or minimizing the alternative explanations that are supported by the same physical evidence. The role of the internet in the popularization and the discussion of the Baghdad Battery has been particularly significant. The artifact is one of the most frequently discussed items in the online alternative history community, where it is often cited as evidence of advanced ancient technology. The online discussions, while they have increased public awareness of the artifact, have also contributed to the spread of misinformation and to the blurring of the distinction between established fact and speculative interpretation. The scholarly community's efforts to maintain a clear distinction between what is known and what is speculated about the Baghdad battery have been complicated by the online popularization, which tends to favor dramatic interpretations over cautious ones. The geography of the region where the Baghdad battery was found deserves careful attention because the natural resources of the area are directly relevant to the evaluation of the various hypotheses about the artifact's function. The area around Baghdad, and more broadly the alluvial plain of central and southern Mesopotamia, is one of the most resource-rich regions of the ancient world. The Tigris and the Euphrates rivers provide water for agriculture and for other purposes. The alluvial soils of the river valleys are among the most fertile in the world, and the geological deposits of the region include a variety of minerals and materials that were exploited by the ancient inhabitants for industrial, commercial, and domestic purposes. The petroleum deposits of Mesopotamia, which are among the largest in the world, were known and exploited in the ancient world, though on a much smaller scale than in the modern era. The natural seeps of bitumen, or asphalt, that occur in various parts of Iraq were used by the ancient Mesopotamians for a wide range of purposes, including waterproofing, adhesion, building construction, and the preservation of perishable materials. The bitumen that was used in the Baghdad battery was almost certainly obtained from one of these natural seeps, and its use in the artifact is consistent with the long-standing Mesopotamian tradition of bitumen exploitation. The copper deposits that were available to the ancient Mesopotamians were obtained primarily from the mountainous regions to the north and the east of the alluvial plain, including the areas of modern Kurdistan, Iran, and Oman. The copper trade was one of the oldest and most important trade relationships in the ancient Near East, and the importation of copper and copper products into the alluvial plain of Mesopotamia was a major component of the region's commercial economy. The copper cylinder of the Baghdad battery was almost certainly made from imported copper, processed in a local workshop using techniques that were well established in the Mesopotamian metalworking tradition. The iron deposits that were available to the ancient Mesopotamians were obtained from similar sources, and the iron industry of the Parthian period, while it was less extensively documented than the copper industry, was well established and produced a range of iron tools, weapons, and other objects. The iron rod of the Baghdad battery was almost certainly made from locally processed iron, forged or drawn in a local workshop using standard metalworking techniques. The availability of acidic liquids that could have served as electrolytes for the Baghdad battery is another relevant geographical factor. The Mesopotamian region produced a variety of acidic liquids, including vinegar, which was produced from the fermentation of date juice and other fruit juices, and grape wine, which was imported from the wine-producing regions to the north and the west. Date vinegar, which was one of the most common acidic liquids in the ancient Mesopotamian household, would have been a readily available and inexpensive electrolyte for the Baghdad battery, if the device was used as a battery. The specific clay from which the Baghdad battery's jar was made has been analysed to determine its origin and its composition. The clay is a local alluvial clay, the same type of clay that was used for the production of ordinary domestic pottery in the Parthian period, and its composition does not indicate any special or unusual origin. The ordinariness of the clay is consistent with the hypothesis that the Baghdad battery was a locally produced object made from locally available materials by local craftsmen, rather than an imported luxury item or a product of a specialized industry. The environmental conditions in which the Baghdad battery would have operated, if it was used as a battery, would have influenced its performance. The hot, arid climate of central Iraq would have promoted the evaporation of the liquid electrolyte, reducing the amount of liquid available for the electrochemical reaction and eventually drying out the device. The use of the asphalt seal at the top of the copper cylinder may have been intended to slow the rate of evaporation and to maintain the level of the electrolyte, extending the operational life of the device. Though this interpretation is speculative, the Parthian Empire, within which the Baghdad battery was produced, was a major player in the geopolitics of the ancient world for nearly 500 years, and its technological capabilities, while less well documented than those of the Roman Empire or the Han dynasty, were substantial. The Parthians were skilled metalworkers, producing arms, armor, coins, and decorative objects of high quality, and they maintained trade relationships with virtually every major civilization in the ancient world, from Rome in the west to China in the east. The cultural eclecticism of the Parthian Empire, which incorporated elements of Greek, Persian, Mesopotamian, and Central Asian traditions, created an intellectual environment in which technological innovation from diverse sources could be combined and adapted. The coinage of the Parthian Empire, which has been extensively studied by numismatists, provides evidence of the Parthians' metallurgical capabilities. The Parthian coins, which were produced in silver, bronze, and occasionally gold, demonstrate a sophisticated understanding of the properties of metals and of the techniques of minting, and the quality of the coins is comparable to the best coinage of the contemporary Roman and Greek worlds. The production of coinage required the ability to alloy metals in specific proportions, to cast or strike coins with specific weights and dimensions, and to produce surfaces of consistent quality, all of which are skills that are consistent with the level of metalworking expertise that would have been needed to produce the Baghdad battery. The ceramic traditions of the Parthian period are also relevant because the Baghdad battery is at its most basic level a ceramic object, a clay jar that was produced using the pottery-making techniques of the period. The pottery of the Parthian period, which has been studied by ceramicists and archaeologists, displays a range of forms and a range of qualities that indicate a sophisticated and well-organized pottery industry. The specific type of pottery to which the Baghdad battery jar belongs has been identified as a common domestic ware, a plain, utilitarian pottery that was produced in large quantities for everyday use. The identification of the jar as a common domestic ware has been used by both the proponents and the critics of the battery hypothesis. By the proponents, who argue that the use of a common jar as the container for a battery is consistent with the practical, utilitarian character of the device, and by the critics, who argue that the ordinariness of the jar is more consistent with its use as a simple storage vessel than as a specialized technological device. The written sources of the Parthian period, which include both the native Parthian sources, written primarily in Aramaic and in Parthian, and the Greek and Roman sources that describe the Parthian Empire from the outside, do not contain any references to electrical devices or to electrical phenomena. The Parthian sources that have survived are primarily administrative documents, legal texts, and religious writings, and they do not provide detailed descriptions of the technological practices of the period. The Greek and Roman sources, which describe the Parthian Empire primarily in the context of military and diplomatic relations, provide limited information about the internal technological life of the empire. The absence of references to electrical technology in the surviving sources does not prove that the Parthians were ignorant of electricity, but it does mean that the claim of Parthian electrical knowledge must rest on the physical evidence of the Baghdad battery alone. The relationship between the Baghdad battery and the broader tradition of Mesopotamian technological innovation is a theme that deserves emphasis. Mesopotamia, which has been described as the cradle of civilization, was the region in which many of the most fundamental technologies of human civilization were first developed. The invention of writing, which occurred in Mesopotamia in approximately 3,400 years before the Common Era, was one of the most transformative innovations in human history. The development of mathematics, including the sexagesimal number system that is the basis of our measurement of time and angles, was a Mesopotamian achievement. The development of astronomy, including the identification of the planets, the prediction of eclipses, and the compilation of star catalogues, was a Mesopotamian achievement. The development of metallurgy, including the smelting of copper, the alloying of bronze, and the forging of iron was an achievement in which the Mesopotamian metalworkers played a central role. The Baghdad battery, if it was a battery, would represent another entry in this long list of Mesopotamian firsts, a discovery of the electrochemical phenomenon that would take its place alongside the other groundbreaking innovations that originated in the region. The significance of this potential addition to the Mesopotamian list of firsts is not merely historical. It would demonstrate that the process of fundamental technological discovery, the discovery of new physical phenomena, and the development of practical applications for them was not limited to the specific cultural and intellectual conditions of the European Enlightenment, but could occur in any civilization that possessed the materials, the skills, and the curiosity to explore the properties of the natural world. The question of the relationship between the Baghdad battery and the broader phenomenon of ancient electricity is one that has been explored by researchers who have investigated whether other civilizations in the ancient world produced artifacts or left records that might indicate knowledge of electrical phenomena. The investigation has revealed that while no other artifact from the ancient world has been identified as an electrical device with the specificity of the Baghdad battery, several ancient civilizations demonstrated an awareness of electrical phenomena, primarily through their knowledge of static electricity and of the electrical properties of certain fish. The ancient Egyptian knowledge of the electric catfish, known as the thunderer of the Nile, is documented in several ancient Egyptian sources, and depictions of the fish appear in Egyptian tomb paintings and reliefs. The electric catfish, which can produce electric shocks of up to 400 volts, was known to the Egyptians for its unusual ability to stun prey and to deliver a painful shock to humans who handled it. The Egyptians appear to have used the fish for medical purposes, applying it to the body of patients suffering from pain, a practice that is documented in Egyptian medical texts and that represents one of the earliest known uses of electrical stimulation for therapeutic purposes. The ancient Greek knowledge of static electricity, which was produced by rubbing amber against cloth, has already been mentioned, and the Greek investigations of this phenomenon, while they did not lead to the development of electrical technology, demonstrate an awareness of electrical phenomena that was part of the broader intellectual culture of the ancient Mediterranean world. The Roman writer Pliny the Elder described the properties of amber, including its ability to attract small objects when rubbed, and the phenomenon was discussed by several other ancient writers, though none of them developed a systematic understanding of the nature of the electrical charge that was being produced. The question of what other technologies the Parthian-era Mesopotamians might have possessed that have not been preserved in the archaeological record is one that the Baghdad battery forces us to consider. The archaeological record of the Parthian period is far from complete, and the technologies that are documented by the surviving evidence are almost certainly only a fraction of the technologies that the Parthian civilization possessed. The perishable technologies, those that used materials such as wood, cloth, leather, and organic fibers that do not survive well in the archaeological record, are largely invisible to us, and the specific functions that these perishable technologies served can only be inferred from the contexts in which their more durable components are found. The core problem with the Baghdad battery is not whether it can produce electricity. It can. Multiple experiments with replicas of the artifact have confirmed that the specific arrangement of copper, iron, and an acidic electrolyte that is found in the Baghdad battery is capable of producing a small but measurable electrical current. The core problem is whether it was intended to produce electricity. The question is not one of physics but of archaeology, not of capability but of purpose, not of what the artifact can do but of what it was made to do. The distinction between capability and purpose is crucial because many objects are capable of doing things that they were not designed to do. A clay pot can be used as a weapon, but that does not mean it was designed as a weapon. A piece of amber can attract small objects when rubbed, but that does not mean it was designed as an electrical device. The Baghdad battery is capable of producing electricity, but the capability does not, by itself, prove that the artifact was designed for that purpose. The proof of purpose requires evidence beyond the mere capability, evidence that the artifact was used in a context that is consistent with an electrical application, evidence that the people who made it understood the electrical properties of the device, and evidence that the electrical output of the device served a practical function that justified the effort of its construction. This evidence is what is missing from the Baghdad battery debate. The physical evidence of the artifact itself tells us what the object is: a clay jar containing a copper cylinder and an iron rod sealed with asphalt, but it does not tell us what the object was used for. The archaeological context, which might have provided evidence of function, has been lost or incompletely recorded, and the literary record of the Pantheon period, which might have contained references to the use of electrical devices, contains no mention of electricity, batteries, or any related technology. The experimental evidence that the Baghdad battery can produce electricity has been provided by multiple researchers who have constructed replicas of the artifact and tested them with various electrolytes. The first widely publicized experiment was conducted by Willard Gray, a technician at the General Electric Laboratory in Pittsfield, Massachusetts, in 1940, just 2 years after Koenig's initial identification of the artifact. Gray constructed a replica of the Baghdad battery, filled it with a copper sulfate solution, and measured a voltage of approximately 1.5 to 2 volts. Subsequent experiments by other researchers, using a variety of electrolytes including vinegar, grape juice, citric acid solution, and wine, have confirmed Gray's results, producing voltages in the range of 1/2 to 2 volts, depending on the specific electrolyte used. The television show Mythbusters conducted a widely publicized experiment with replicas of the Baghdad battery in 2005, in which they constructed 10 replica batteries and connected them in series, producing a total voltage of approximately 4 volts. They then used this voltage to electroplate a small object with a thin layer of gold, demonstrating that the Baghdad battery could, in principle, be used for electroplating. The experiment was successful in demonstrating the electroplating capability of the device, but it did not prove that the ancient users of the Baghdad battery actually used it for this purpose. But here is the problem. The electroplating hypothesis, while it is the most widely discussed application of the Baghdad battery, has several significant weaknesses that have been identified by critics. The first weakness is that the voltage and the current produced by a single Baghdad battery are very small, and the electroplating of an object of any significant size would require either a very long time, measured in hours or days, or the use of multiple batteries connected in series or in parallel. The use of multiple batteries would require a level of understanding of electrical circuits. The knowledge that batteries could be connected to increase their voltage or their current that is not documented in any surviving Parthian-era source. The second weakness of the electroplating hypothesis is that the ancient metalworkers of the Near East already possessed effective techniques for applying precious metal coatings to objects, including fire gilding, leaf gilding, and depletion gilding, all of which were simpler, faster, and more reliable than electroplating with a Baghdad battery. The advantage of electroplating over these existing techniques would have been marginal at best, and it is difficult to explain why the ancient metalworkers would have developed an electrical technique when they already possessed non-electrical techniques that were effective for the same purpose. The third weakness is the absence of any residual evidence of electroplating on objects that have been found in association with the Baghdad battery artifacts. If the batteries were used for electroplating, we would expect to find electroplated objects at the same archaeological site, and we would expect the electroplated coating to exhibit the characteristic microscopic features that distinguish electroplated coatings from coatings applied by other techniques. No such objects have been identified, though the incomplete excavation and documentation of the Qujut Rabu site means that the absence of evidence is not in this case strong evidence of absence. And it gets worse for the battery hypothesis. The alternative explanations for the Baghdad battery's function, while they are less dramatic and less attention-grabbing than the battery hypothesis, are in many ways more consistent with the available evidence. The The most widely cited alternative explanation is that the clay jars were used for the storage of sacred scrolls or documents, with the copper cylinder serving as a protective container for the scroll and the asphalt serving as a seal to protect the contents from moisture and decay. This interpretation is consistent with the archaeological evidence of similar scroll storage containers from other sites in the ancient Near East, and it does not require the assumption that the Parthian-era Mesopotamians possessed knowledge of electricity. Another alternative explanation is that the jars were used for the storage of organic substances, such as medicines, perfumes, or oils, and that the copper cylinder and the iron rod were components of a sealing or dispensing mechanism rather than an electrical device. The corrosion of the iron rod, which Koenig interpreted as evidence of exposure to an acidic electrolyte, could also be explained by the long-term exposure of the iron to moisture and to the mildly acidic conditions that develop in a sealed container containing organic matter that is slowly decomposing. A third alternative explanation, proposed by the archaeologist St. John Simpson of the British Museum, is that the jars were used in a magico-medical context, possibly for the application of a mild electrical sensation to the body for therapeutic or ritual purposes. Simpson has noted that the Parthian-era Near East had a tradition of using various substances, techniques for medical and magical purposes, and the production of a tingling electrical sensation, similar to the sensation produced by the torpedo ray, would have been consistent with this tradition. This interpretation has the advantage of providing a plausible use for the electrical output of the battery, without requiring the assumption that the ancients understood the physics of electricity, or that they used the device for industrial applications, such as electroplating. The question of how many Baghdad battery artifacts exist is itself a matter of some uncertainty. Koenig described several artifacts from the Qujut Rebu site, but the exact number and the specific condition of each artifact are not clearly documented in the surviving records. Some accounts describe as many as 12 similar artifacts, while others describe fewer. The uncertainty about the number of artifacts compounds the uncertainty about their function, because the existence of multiple similar artifacts would suggest that the objects were part of a standardized production, a fact that would be more consistent with a practical function than with a one-off experimental curiosity. The dating of the Baghdad battery has also been the subject of debate. The original dating of the artifacts to the Parthian period, roughly the 1st century before the Common Era to the 2nd century of the Common Era, was based on the pottery style and the stratigraphy of the Qujut Rebu site. However, some researchers have proposed a later date, placing the artifacts in the Sassanid period, roughly the 3rd to the 7th century of the Common Era, based on a re-evaluation of the pottery and the associated finds. The uncertainty about the dating does not fundamentally affect the significance of the artifacts, because the key question, whether they were used as electrical devices, is independent of whether they were made in the Parthian or the Sassanid period. But the dating does affect the cultural context in which the artifacts must be interpreted, because the Parthian and the Sassanid periods had different cultural, religious, and technological characteristics that might influence the interpretation of the artifact's function. The loss of the original artifacts during the looting of the National Museum of Iraq in April of 2003 was a catastrophic blow to the study of the Baghdad battery. The looting, which occurred during the American invasion of Iraq, resulted in the theft or the destruction of thousands of artifacts from the museum's collection, including some of the artifacts that had been associated with the Baghdad battery. The loss of these artifacts means that some of the scientific analyses that could have been conducted on the original objects, including detailed chemical analysis of the residues inside the copper cylinder, which might have identified the specific electrolyte that was used, can no longer be performed. The loss of the original evidence is a permanent and irreversible setback for the study of the Baghdad battery, and it is a reminder of the fragility of the archaeological record and of the importance of protecting cultural heritage from the ravages of war and looting. The broader question of what the Baghdad battery tells us about the technological capabilities of the ancient world is one that must be considered carefully and without prejudice. The artifact is extraordinary, regardless of whether it was used as a battery or for some other purpose. The specific arrangement of copper, iron, and asphalt inside the clay jar is unusual and is not easily explained by any of the standard archaeological categories of ancient artifacts. The debate about the artifact's function has stimulated important research into the history of electrochemistry, the metallurgical traditions of the ancient Near East, and the cultural practices of the Parthian and Sassanid periods, and the questions that the artifact raises about the limits of ancient technology, about the relationship between capability and purpose, and about the nature of technological progress, are questions that are worth asking, regardless of whether the final answer turns out to be battery, scroll jar, or something else entirely. But here is what makes this truly terrifying. Whether or not the Baghdad battery was used to produce electricity, the fact that the specific arrangement of components inside the jar is capable of producing electricity raises the possibility that the electrochemical phenomenon was discovered in the ancient world, whether deliberately or accidentally, and that this discovery was not preserved in the historical record. The history of technology is full of examples of discoveries that were made and then lost, technologies that were developed and then forgotten, capabilities that existed for a time and then disappeared from the body of human knowledge. If the Baghdad battery represents such a discovery, it would be one of the most significant examples of lost technological knowledge in human history, because it would demonstrate that the fundamental phenomenon of electrochemistry, the conversion of chemical energy into electrical energy, was known nearly 2 millennia before it was rediscovered by Volta. The physical description of the Baghdad battery deserves more detailed examination, because the specific features of the artifact are the primary evidence on which all interpretations are based. The clay jar that forms the outer container of the artifact is a common type of Parthian-era pottery, unremarkable in its form and its fabric, the kind of vessel that was used for a wide range of domestic and commercial purposes in the ancient Near East. The jar is approximately 15 centimeters tall and approximately 8 centimeters in diameter at its widest point, with a narrow mouth that would have been sealed with a stopper of asphalt or of some other material. Inside the jar is a copper cylinder that is approximately 9 centimeters tall and approximately 2.6 centimeters in diameter. The copper cylinder is made from a single sheet of copper that has been rolled into a tube, with the edges of the sheet overlapping slightly and soldered or crimped together to form a watertight seal. The bottom of the copper cylinder is sealed with a disc of copper that has been soldered to the tube, creating a closed container within the clay jar. The iron rod that is the third component of the artifact is approximately 7.5 centimeters long and approximately 1 centimeter in diameter. The rod is positioned in the center of the copper cylinder, held in place by the asphalt plug that seals the top of the cylinder. The asphalt plug serves the dual function of sealing the top of the cylinder and of insulating the iron rod from the copper, preventing direct contact between the two metals. The insulation of the iron from the copper is a critical feature of the artifact, because the production of an electrochemical reaction requires that the two metals be separated by an electrolyte rather than being in direct metallic contact. The careful arrangement of the components, with the iron rod centered in the copper cylinder and insulated from it by the asphalt plug, is the feature of the artifact that most strongly suggests a deliberate design rather than an accidental arrangement. The insulation of the two metals from each other, while allowing them to be connected through an electrolyte, is the essential design feature of a galvanic cell, and its presence in the Baghdad battery is the strongest argument in favor of the battery hypothesis. The counter-argument, which has been made by the proponents of the alternative interpretations, is that the arrangement of the components could serve other functions as well. The copper cylinder could be a protective container for a scroll or other document, with the iron rod serving as an axle around which the scroll was wound, and the asphalt plug serving as a seal to protect the contents from moisture and decay. The copper cylinder could also be a container for a liquid medicine or a perfume, with the iron rod serving as a stirring implement or a dispensing device, and the asphalt plug serving as a closure. These alternative interpretations, while they do not explain why the iron rod would need to be insulated from the copper by the asphalt plug, do provide plausible functions for the individual components that do not require the assumption of electrical knowledge. The question of whether the insulation of the iron from the copper is a deliberate design feature or an incidental consequence of the construction method is a key point of contention in the debate. The proponents of the battery hypothesis argue that the insulation is deliberate and that it demonstrates an understanding of the need to separate the two metals in order to produce an electrochemical reaction. The proponents of the alternative hypotheses argue that the asphalt plug was used simply as a seal, and that the insulation of the iron from the copper was an incidental effect of the sealing method rather than a deliberate design feature. The broader tradition of metalwork in the Parthian and Sassanid periods provides comparative evidence that is relevant to the electroplating hypothesis. The metalwork of the Parthian period includes a significant number of objects that have been described as having a gold or silver surface coating that is unusually thin and uniform, prompting some researchers to suggest that the coating may have been applied by electroplating rather than by the traditional techniques of fire gilding or leaf gilding. The analysis of these coated objects using modern analytical techniques, including scanning electron microscopy and energy dispersive X-ray spectroscopy, has produced mixed results. Some studies have reported that the coatings on certain Parthian-era objects exhibit features that are more consistent with electroplating than with fire gilding or leaf gilding, including an unusually uniform thickness and a strong adhesion to the underlying metal. Other studies have reported that the coatings are consistent with traditional gilding techniques, and that the features that were initially interpreted as evidence of electroplating can be explained by the specific application methods that were used in the traditional techniques. The debate about the nature of the surface coatings on Parthian-era metalwork mirrors the broader debate about the Baghdad battery itself. The physical evidence is ambiguous, the interpretations are divided, and the contextual information that would resolve the ambiguity is missing. The resolution of the debate about the coatings would have important implications for the Baghdad battery debate, because the identification of electroplated coatings on Parthian-era objects would provide strong indirect evidence that the Baghdad battery was used for electroplating, while the absence of such coatings would weaken the electroplating hypothesis. The study of the gold and silver coating techniques used in the ancient Near East has been an active area of research in archaeometallurgy, the field that applies the tools of modern materials science to the study of ancient metals and metalworking techniques. The archaeometallurgical analysis of ancient coated objects has revealed that the ancient metalworkers used a wider range of coating techniques than was previously recognized, and that the specific technique used for a particular object can often be determined by the microstructural features of the coating and the interface between the coating and the underlying metal. The development of standardized analytical protocols for distinguishing electroplated coatings from coatings fangs applied by other techniques is an ongoing effort within the archaeometallurgical community. The protocols involve the examination of the coating at high magnification using electron microscopy, the analysis of the composition of the coating and the interface using spectroscopic techniques, and the comparison of the observed features with the features that are known to be produced by different coating techniques. The application of these protocols to the Parthian-era metalwork has the potential to provide definitive evidence for or against the electroplating hypothesis, though the results that have been obtained so far are inconclusive. The question of whether the Parthian-era Mesopotamians had any theoretical understanding of the electrical phenomenon that the Baghdad battery could produce is one that cannot be answered from the surviving textual evidence. The cuneiform texts of the Parthian period, which are the primary literary source for the intellectual life of the period, do not contain any references to electricity, to electrochemistry, or to any phenomenon that could be interpreted as an electrical effect. The absence of such references does not prove that the Mesopotamians were unaware of the phenomenon, because the cuneiform texts are a selective record that does not document every aspect of Mesopotamian knowledge and practice. But the absence of textual evidence does mean that the claim of Mesopotamian electrical knowledge rests entirely on the physical evidence of the Baghdad battery itself, without any corroboration from the literary record. The question of whether the Mesopotamians could have observed the electrical phenomenon without understanding it is a more interesting and a more plausible question. The electrochemical reaction that occurs in a galvanic cell produces several observable effects, including the corrosion of the anode, the warming of the electrolyte, the production of gas bubbles at the electrodes, and, if the circuit is completed through the human body, a tingling or prickling sensation. Any of these effects could have been observed by an ancient craftsman who happened to immerse two different metals in an acidic solution, and the observation of these effects could have led to the deliberate construction of a device that replicated and amplified them. The scenario of accidental discovery is particularly plausible in the context of the ancient metalworking tradition. The ancient metalworkers routinely immersed metal objects in acidic solutions for purposes such as cleaning, etching, and surface treatment, and the accidental immersion of two different metals in the same acidic bath would have produced the electrochemical effects that characterize a galvanic cell. A metalworker who noticed that a copper object and an iron object, when simultaneously immersed in a vinegar bath, produced a tingling sensation when touched, might well have been curious enough to investigate the phenomenon further. And the investigation might have led to the deliberate construction of a device that replicated the effect. The plausibility of the accidental discovery scenario is strengthened by the simplicity of the materials involved. Copper, iron, and vinegar are common materials that were available to every metalworker in the ancient Near East, and the electrochemical reaction that occurs between them is a spontaneous reaction that does not require any special conditions or any special knowledge to initiate. The discovery of the electrochemical phenomenon would therefore have been accessible to any metalworker who happened to observe the effects of immersing dissimilar metals in an acidic solution, and the probability of such an observation occurring, given the large number of metalworkers and the long period of metalworking practice in the ancient Near East, is not negligible. The question of why the discovery, if it was made, was not developed further is a more difficult question. The electrochemical phenomenon, once discovered, could have been developed in many directions, including the production of larger voltages through the series connection of multiple cells, the deposition of metals through electrolysis, and the production of chemical effects through the passage of current through various solutions. The absence of evidence for any of these developments in the archaeological record of the ancient Near East is a significant challenge for the battery hypothesis, because it suggests that either the discovery was not made, or that it was made but not developed or not transmitted to subsequent generations. The possibility that the discovery was made but not developed is consistent with the broader pattern of technological stagnation that characterized the ancient world in certain domains. The ancient world produced many discoveries that were not developed to their full potential, including Hero of Alexandria's steam engine, which was used as a toy or a demonstration device, but was not developed into a practical power source. The Baghdad battery, if it was a battery, might similarly have been a curiosity, a device that produced an interesting effect, but that was not developed into a practical technology because the potential applications were not recognized, or because the cultural and economic conditions did not favor the development of electrical technology. The investigation of the corrosion products on the iron rod of the Baghdad battery provides additional evidence that is relevant to the evaluation of the various hypotheses. The corrosion of the iron rod is significant because the specific types and the specific distributions of the corrosion products can provide information about the chemical environment to which the iron was exposed during the artifact's use. If the iron was exposed to an acidic electrolyte, as the battery hypothesis requires, the corrosion products should include specific phases and specific distributions that are consistent with electrochemical corrosion. If the iron was simply exposed to moisture and air, as the alternative hypotheses suggest, the corrosion products should be consistent with ordinary atmospheric corrosion. The distinction between electrochemical corrosion and atmospheric corrosion is, in principle, detectable through careful analysis of the corrosion products. Electrochemical corrosion produces a specific pattern of corrosion that is concentrated at the interface between the iron and the electrolyte, and the corrosion products are typically arranged in layers that reflect the progressive dissolution of the iron into the electrolyte. Atmospheric corrosion, by contrast, produces a more uniform pattern of corrosion that affects the entire exposed surface of the iron, and the corrosion products are typically a mixture of iron oxides and iron hydroxides that form a loose, powdery coating on the surface. The limited analyses that have been conducted on the corrosion products of the Baghdad battery's iron rod have not produced a definitive distinction between electrochemical and atmospheric corrosion, partly because the long period of burial, approximately 2,000 years, has obscured the original corrosion pattern, and partly because the analytical techniques that were used were not sophisticated enough to distinguish between the two types of corrosion. The application of more advanced analytical techniques, such as cross-sectional scanning electron microscopy and micro-Raman spectroscopy, to the corrosion products could potentially provide a more definitive answer, but the loss of the original artifacts during the looting of the Baghdad Museum has made such analysis impossible on the original objects. The analysis of corrosion products on replicas of the Baghdad battery that have been operated under controlled conditions and then allowed to age has been proposed as an alternative approach to the problem. By comparing the corrosion products on a replica that has been used as a battery with the corrosion products on a replica that has been used as a storage vessel, researchers could potentially identify the specific features that distinguish electrochemical corrosion from atmospheric corrosion, and could then look for those features on the original artifacts if they are ever recovered. This experimental approach has been proposed but has not yet been fully implemented. The question of whether any residual traces of the electrolyte might be preserved within the copper cylinder or the clay jar is another avenue of investigation that could potentially provide evidence for the battery hypothesis. If the jar was filled with an acidic liquid, traces of the liquid, including dissolved salts, organic acids, and other chemical species, might be preserved in the porous fabric of the clay or in the corrosion products on the metal surfaces. The detection of such traces would provide direct evidence that the jar contained an acidic liquid, which would support the battery hypothesis, while the absence of such traces would be consistent with either hypothesis, since the traces could have been lost through leaching or decomposition during the long period of burial. The analysis of the asphalt seal at the top of the copper cylinder has provided additional information about the construction of the artifact. The asphalt has been identified as a natural bitumen, consistent with the bitumen deposits that are found in several regions of Iraq. The asphalt was applied in a molten state and was allowed to harden, forming a tight seal around the iron rod and between the iron rod and the copper cylinder. The quality of the seal, which effectively isolates the iron from the copper and which provides a watertight closure for the top of the cylinder, is consistent with both the battery hypothesis, which requires the insulation of the iron from the copper, and the storage hypothesis, which requires the sealing of the contents of the cylinder against moisture and air. The investigation of the relationship between the Baghdad battery and ancient religious and magical practices has been an important dimension of the research because the Parthian and Sassanid periods were characterized by a rich and complex religious landscape that included elements of multiple traditions and that incorporated a wide range of ritual practices. The possibility that the Baghdad battery was used in a religious or magical context, perhaps for the production of a sensation or an effect that was interpreted as a manifestation of divine or supernatural power, has been explored by several researchers who specialize in the religious history of the ancient Near East. The Parthian religious landscape included Zoroastrianism, the ancient Iranian religion that emphasized the cosmic struggle between the forces of good and evil, between light and darkness. The Zoroastrian tradition incorporated fire worship and various ritual practices that involved the manipulation of natural phenomena and the production of an unusual physical effect, such as the tingling sensation that a Baghdad battery could produce, would have been consistent with the Zoroastrian interest in the manifestation of divine power through natural means. The Mesopotamian magical tradition, which had roots stretching back thousands of years before the Parthian period, included a wide range of practices that were designed to invoke supernatural forces and to produce specific effects on the physical world. The magical texts that have survived from the ancient Near East describe procedures that involve the use of specific materials, specific words, and specific physical manipulations to produce effects that were believed to be the manifestation of supernatural power. The use of a Baghdad battery in a magical context, perhaps to produce a sensation that was interpreted as the touch of a deity or a spirit, would have been consistent with the broader Mesopotamian magical tradition. The Greek magical tradition, which was known in the Parthian-era Near East through the spread of Hellenistic culture, also included practices that involved the use of physical phenomena for magical purposes. The Greek magical papyri, a collection of magical texts from the Greco-Roman period that includes spells, incantations, and instructions for the production of various magical effects, describe procedures that involve the use of specific materials and specific physical manipulations to produce effects that were believed to have supernatural significance. The possibility that the Baghdad battery was used in a Greek-influenced magical tradition, perhaps for the production of an effect that was described in a magical text that has not survived, is one that has been considered by researchers. The distinction between magical and technological uses of the Baghdad battery may be a false dichotomy in the context of the ancient world, because the ancient understanding of natural phenomena did not draw the same sharp distinction between natural and supernatural causation that characterizes the modern worldview. In the ancient world, the production of an unusual physical effect, whether by chemical, mechanical, or electrical means, was likely to be interpreted within a framework that included both natural and supernatural elements, and the use of a device like the Baghdad battery for what we would call a technological purpose, such as electroplating, might have been accompanied by rituals, prayers, and other practices that placed the technology within a broader magical or religious context. The possibility that the Baghdad battery was used for both technological and magical purposes simultaneously, for electroplating in a context that was accompanied by ritual observances, or for the production of a sensation in a context that combined therapeutic and religious elements, is one that has been considered by researchers who recognize the complexity of the ancient understanding of causation and the difficulty of separating technology from magic in the context of the ancient world. The investigation of the religious context of the Baghdad battery has been hampered by the same factors that have hampered the investigation of the technological context. The incompleteness of the archaeological record, the loss of the original artifacts, and the absence of textual references to the artifact or to its function. The religious interpretation of the Baghdad battery, like the technological interpretation, remains a hypothesis that is consistent with the available evidence, but that cannot be confirmed or refuted with the evidence currently available. The question of whether the Baghdad battery could have been used for the production of ozone or of other chemical species through the electrolysis of the acidic electrolyte is one that has been raised by some researchers. The electrolysis of water, which occurs when an electrical current is passed through water, produces hydrogen gas at the cathode and oxygen gas at the anode. In the case of the Baghdad battery, the electrolysis of the acidic electrolyte would produce hydrogen at the iron rod and oxygen at the copper cylinder, along with other chemical species depending on the specific composition of the electrolyte. The production of gas bubbles at the electrodes would have been a visible and potentially dramatic effect that could have been observed by the users of the device, and it is possible that this effect rather than any electrical application, was the purpose of the device. The production of visible gas bubbles at the electrodes of a Baghdad battery has been confirmed by experimental replications, which have shown that bubbles form at both the iron and the copper surfaces when the device is operated with an acidic electrolyte. The bubbling effect, which would have been visible through the mouth of the jar if the asphalt seal was not in place, would have appeared to the ancient observer as though the liquid was boiling, or as though some invisible force was agitating the surface of the liquid, an effect that could have been interpreted as a manifestation of supernatural power, or as a sign of the efficacy of a magical or medical treatment. The possibility that the Baghdad battery was used for a gas production application is an alternative to the electroplating hypothesis that has not been widely discussed in the literature, but that deserves consideration. The production of gas through the electrolysis of water is one of the most easily observable effects of an electrical current, and it is an effect that would have been accessible to the users of the Baghdad battery without any external circuit or any specialized equipment. The gas production hypothesis has the advantage of providing a visible and dramatic effect that could have been used in a ritual, medical, or demonstration context, without requiring the assumption of industrial applications such as electroplating. The investigation of the specific chemical effects that the Baghdad battery could produce under various conditions has been conducted through laboratory experiments that have tested the device with a range of electrolytes and a range of operating conditions. The results have shown that the device can produce a variety of chemical effects, including the corrosion of the iron anode, the deposition of metallic copper on the cathode in some electrolyte systems, the production of gas bubbles at both electrodes, and the warming of the electrolyte due to the exothermic nature of the electrochemical reaction. Each of these effects is a potential function of the device, and the identification of the specific effect that the ancient users exploited, if any, requires contextual evidence that is currently unavailable. The study of the specific electrolytes that would have been available to the ancient users of the Baghdad battery has been an important aspect of the experimental investigation. The candidate electrolytes that have been tested include vinegar, which was widely available in the ancient Near East, and which is a dilute solution of acetic acid, grape juice and wine, which contain tartaric acid and other organic acids, citrus juice, which contains citric acid, and date juice, which was one of the most common acidic liquids in the ancient Mesopotamian household. The experiments have shown that all of these candidate electrolytes are capable of supporting the electrochemical reaction between the iron and the copper, producing voltages and currents that are similar to those produced by modern electrolytes, and any of them could have served as the electrolyte in the Baghdad battery. The question of how the ancient users of the Baghdad battery might have discovered the optimal electrolyte for their purposes is one that can be addressed through the scenario of accidental discovery that we have already discussed. A metalworker who was using an acidic liquid for cleaning or for etching metal objects might have noticed that the liquid produced unusual effects when it was in contact with both copper and iron simultaneously, and the investigation of these effects might have led to the identification of the specific liquids that produced the strongest or the most useful effects. The optimization of the electrolyte through trial and error, testing different liquids and observing the results, is the kind of empirical investigation that was well within the capabilities of the ancient metalworkers, and that is consistent with the broader Mesopotamian tradition of empirical inquiry. The investigation of the relationship between the Baghdad battery and ancient practices of pain relief and medical treatment adds yet another dimension to the interpretation debate. The investigation of the Baghdad battery has been conducted by researchers from a wide range of disciplines, including archaeology, chemistry, materials science, electrical engineering, and ancient history, and it has produced a body of knowledge and a body of debate that spans nearly 9 decades. The investigation has proceeded along several distinct tracks, each of which has produced important results, and each of which has raised new questions about the artifact and the technology that may have produced it. The first major track of investigation has been the experimental replication of the Baghdad battery using modern materials and ancient compatible materials to determine whether the artifact can produce a measurable electrical current. The experimental replications, which have been conducted by dozens of researchers and amateur experimenters since Willard Gray's initial experiment in 1940, have consistently confirmed that the specific arrangement of copper, iron, and an acidic electrolyte that characterizes the Baghdad battery is capable of producing a voltage of approximately 1/2 to 2 volts, depending on the specific electrolyte and the specific conditions of the experiment. The experiments of Arne Egebrecht, the director of the Roma and Pelizaeus Museum in Hildesheim, Germany, which were conducted in the 1970s and 80s, are among the most cited and most controversial in the history of the Baghdad battery research. Egebrecht claimed to have used replicas of the Baghdad battery to electroplate small objects with a thin layer of gold, demonstrating that the artifact could have been used for decorative electroplating. Egebrecht's experiments were widely publicized and were cited by many subsequent writers as evidence that the Baghdad battery was used for electroplating in the ancient world. However, Egebrecht's experiments have been criticized on several grounds. The specific conditions of his experiments, including the electrolyte that he used and the duration of the electroplating process, were not published in a peer-reviewed scientific journal, and the details of his experimental protocol are not available for independent verification. Some critics have argued that Egebrecht used a gold cyanide solution as his electrolyte, a substance that was not available in the ancient world, and that would have been necessary for the efficient electroplating of gold. The use of a non-ancient electrolyte would undermine the relevance of the experiment for the question of whether the ancient users of the Baghdad battery could have performed electroplating, because the experiment would demonstrate only that modern electroplating could be performed with the Baghdad battery, not that ancient electroplating could have been. The more carefully controlled experiments that have been conducted by subsequent researchers have produced more nuanced results. These experiments have shown that electroplating with a Baghdad battery is possible in principle, but extremely slow and inefficient. The deposition of a visible layer of gold on an object using a single Baghdad battery and an ancient compatible electrolyte, such as a solution of gold dissolved in vinegar or in grape juice, would require hours or days of continuous operation, and the quality of the resulting coating would be inferior to the coatings that could be produced by the traditional non-electrical techniques that were available to the ancient metalworkers. The second major track of investigation has been the chemical analysis of the artifacts themselves, aimed at identifying the specific substances that were present inside the copper cylinder, and that might indicate the artifact's function. The analysis of the residues inside the copper cylinder could potentially identify the specific electrolyte that was used, if the artifact was used as a battery, or the specific substances that were stored inside the cylinder, if the artifact was used as a storage vessel. The results of the chemical analyses that have been conducted on the original artifacts are not well documented in the published literature, partly because the analyses were conducted before modern analytical techniques were available, and partly because the records of the analyses have been lost or damaged. The analysis of the corrosion products on the iron rod has provided some information about the chemical environment inside the cylinder. The iron rod shows significant corrosion, which is consistent with exposure to an acidic or oxidizing environment over a prolonged period. The corrosion products include iron oxides and iron hydroxides, which are the normal products of iron corrosion in the presence of moisture and oxygen. The presence of these corrosion products is consistent with the battery hypothesis, because the electrochemical reaction in a galvanic cell involves the oxidation of the iron anode, which would produce the same corrosion products that have been observed. But the corrosion is also consistent with the alternative hypothesis of long-term storage, because iron will corrode in the presence of any moisture, regardless of whether an electrochemical reaction is occurring. The third major track of investigation has been the study of the archaeological context of the Baghdad battery artifacts, aimed at determining the specific function that the artifacts served within the broader cultural and economic life of the Parthian-era community that produced them. The archaeological context is the key to determining the function of any artifact, because the function of an object is determined not by its physical properties alone, but by the way it was used within a specific cultural context. A clay pot found in a kitchen is a cooking vessel. The same clay pot found in a temple is a ritual vessel. The physical object is the same, but its function is different depending on the context in which it was used. The archaeological context of the Baghdad Battery is unfortunately poorly documented. The Qhapaq Ñan site, where the artifacts were found, was excavated in the 1930s by Iraqi archaeologists, and the excavation records, while they provide some information about the stratigraphy and the general character of the site, do not provide the detailed contextual information that would be needed to determine the specific function of the battery-like artifacts, the specific building or structure in which the artifacts were found, the specific room or area within that building, the specific objects that were found in association with the artifacts, and the specific layer or level at which the artifacts were deposited are all important contextual details that are either missing from or unclear in the surviving records. The absence of detailed contextual information is one of the most significant obstacles to the resolution of the Baghdad Battery debate, because it prevents researchers from using the most powerful analytical tool available to archaeologists, contextual analysis, to determine the function of the artifacts. Without knowing where the artifacts were found and what they were found with, it is impossible to determine whether they were associated with a metalworking workshop, where their use as electroplating devices would be plausible, or with a temple, where their use as ritual objects would be more likely, or with a domestic dwelling, where their use as storage containers would be the most straightforward interpretation. The fourth major track of investigation has been the comparative study of similar artifacts from other sites in the ancient Near East and beyond, aimed at determining whether the Baghdad Battery is a unique object or a representative of a broader tradition of similar devices. The search for comparable artifacts has produced a small number of possible parallels, though none of them is as clear or as well preserved as the Baghdad Battery itself. Artifacts that have been compared to the Baghdad Battery include copper scroll containers from the Dead Sea region, which share some structural similarities with the Baghdad Battery's copper cylinder, and various small jars and containers from other Near Eastern sites that contain metallic components. The copper scroll containers, which were used to enclose and protect written documents, provide a plausible parallel for the scroll storage interpretation of the Baghdad Battery, because they demonstrate that the use of copper containers for document storage was a known practice in the ancient Near East. The Seleucia vessels, a group of objects found at the ancient site of Seleucia on the Tigris, south of Baghdad, have also been cited as possible parallels for the Baghdad Battery. The Seleucia vessels are small clay jars that contain copper and iron components, similar to the components of the Baghdad Battery, and they have been interpreted by some researchers as additional examples of ancient galvanic cells. However, the Seleucia vessels have not been as extensively studied or as widely discussed as the Baghdad Battery, and their interpretation remains uncertain. The numbers are striking when we consider the range of hypotheses that have been proposed for the function of the Baghdad Battery and the decades of research that have been devoted to evaluating them. At least 5 distinct hypotheses have been seriously proposed: the battery hypothesis, the electroplating hypothesis, the scroll storage hypothesis, the medical or magical hypothesis, and the simple storage hypothesis. Each hypothesis has its strengths and its weaknesses, and none has been definitively confirmed or definitively refuted by the available evidence. The debate has continued for nearly 90 years, involving researchers from multiple countries and multiple disciplines, and the resolution of the debate seems no closer today than it was when Koenig first identified the artifact in 1938. The fifth major track of investigation has been the theoretical analysis of the electrochemical properties of the Baghdad Battery, using the tools of modern electrochemistry to predict the performance of the device under various conditions. The theoretical analysis which is based on the known electrochemical properties of iron and copper in various electrolytes, has confirmed that the Baghdad battery is capable of producing a voltage in the range of 1/2 to 2 volts and a current of a few milliamperes, depending on the specific electrolyte and the specific conditions. The theoretical analysis has also shown that the internal resistance of the device is relatively high, which limits the current that the device can supply and which would make it inefficient for applications that require a significant amount of electrical power. The theoretical analysis has also explored the possibility that the Baghdad battery was used in conjunction with other devices, such as wires, connectors, and external circuits, that would have been needed to deliver the electrical current to a useful application. The absence of any evidence of such ancillary devices in the archaeological record is a significant weakness of the battery hypothesis, because the battery by itself is useless without a means of connecting it to a load. The proponents of the battery hypothesis have argued that the ancillary devices, which would have been made of perishable materials such as wood, cloth, or organic fibers, may have decayed and disappeared from the archaeological record, leaving only the more durable ceramic, copper, and iron components of the battery itself. The sixth major track of investigation has been the analysis of the cultural and religious context of the Parthian period, aimed at identifying the specific cultural practices or beliefs that might explain the function of the Baghdad battery. The Parthian period was characterized by a complex religious landscape that included elements of Zoroastrianism, Babylonian religion, Greek religion, and various local cults and traditions. The possibility that the Baghdad battery was used in a religious or magical context, perhaps for the production of a sensation that was interpreted as a manifestation of divine power, has been explored by several researchers. The use of electrical sensations for medical or magical purposes has a long history in the human world. The torpedo ray, which was known to the ancient Mesopotamians as well as to the Greeks and the Romans, produces an electric shock that was used for therapeutic purposes in the ancient world. The possibility that the Baghdad battery was used to produce a similar sensation, perhaps by applying the electrodes to the body of a patient or a worshipper, is consistent with the known cultural practices of the Parthian period and would provide a plausible explanation for the artifact's function that does not require the assumption of industrial applications such as electroplating. The magico-medical hypothesis has the advantage of explaining both the electrical capability of the device and its apparent limitation. A device that was used to produce a mild electrical sensation would not need to produce a large voltage or a large current, and the small output of a single Baghdad battery would be sufficient for this purpose. The device would not need to be connected to an external circuit, because the sensation could be produced by touching both the copper cylinder and the iron rod simultaneously, completing the circuit through the body of the person who was touching the device. And the device would not leave any physical evidence of its use, because the sensation is a transient phenomenon that does not produce any lasting physical change in the person who experiences it. The role of experimental archaeology in the Baghdad battery debate deserves particular attention because the experimental replication of the artifact has been one of the most productive and most publicized aspects of the research. Experimental archaeology, the practice of replicating ancient technologies using ancient compatible materials and techniques, is a valuable tool for understanding the capabilities and the limitations of ancient technologies, and it has been applied to the Baghdad battery by numerous researchers over the past 9 decades. The basic experimental protocol for replicating the Baghdad battery is straightforward. Construct a clay jar, a copper cylinder, and an iron rod of the appropriate dimensions. Assemble them in the configuration described by Koenig, fill the jar with an acidic electrolyte, and measure the voltage and the current that the device produces. The simplicity of this protocol is one of the reasons why the Baghdad battery experiment has been replicated so many times, and by such a wide range of experimenters, from professional scientists working in university laboratories to amateur enthusiasts working in home workshops. The results of these experiments have been strikingly consistent. The voltage produced by a single Baghdad battery replica using vinegar or grape juice as the electrolyte, is typically in the range of 1/2 to 1.5 volts, with a current of a few milliamperes. The voltage and the current are small but measurable, and they are sufficient to produce observable effects, including the deflection of a galvanometer, the tingling sensation produced by touching the electrodes, and, over extended periods, the electrochemical deposition of metals from solution. The consistency of the experimental results across different experimenters, different materials, and different conditions is significant because it demonstrates that the electrochemical capability of the Baghdad battery is robust and reproducible. The artifact does not need to be constructed with exceptional precision or operated under exceptional conditions to produce an electrical current. The current is produced by the basic electrochemical reaction between the iron and the copper in the presence of the acidic electrolyte, a reaction that occurs spontaneously and that does not require any special skill or knowledge to initiate. The experiments have also explored the effect of different electrolytes on the performance of the device, testing not only the ancient compatible electrolytes such as vinegar and grape juice, but also modern electrolytes such as copper sulfate solution and dilute sulfuric acid. The modern electrolytes produce higher voltages and higher currents than the ancient compatible electrolytes, but the ancient compatible electrolytes produce voltages and currents that are sufficient to demonstrate the electrochemical principle, and that would have been sufficient to produce the effects that the various hypotheses propose. The experiments have also investigated the durability and the stability of the Baghdad battery over time. The electrochemical reaction that produces the current is a consumptive reaction, meaning that it gradually consumes the iron anode and the acidic electrolyte, and the device will eventually stop producing current when the iron is fully corroded or when the electrolyte is fully consumed. The experiments have shown that a single Baghdad battery can produce current for several hours to several days, depending on the specific electrolyte and the specific conditions before the reaction is exhausted. The experiments have also explored the possibility of connecting multiple Baghdad batteries in series to produce a higher voltage or in parallel to produce a higher current. The connection of multiple batteries requires some form of external conductor, such as a wire or a strip of metal, to carry the current from one battery to the next. The experiments have shown that the connection of multiple batteries is effective and that the combined voltage or current is approximately equal to the sum of the individual voltages or currents, as would be expected from the theory of galvanic cells. The question of what the Baghdad battery was not used for is in some ways as instructive as the question of what it was used for. The electrical output of a single Baghdad battery, approximately 1 to 2 volts and a few milliamperes, is far too small for many of the applications that have been suggested by popular writers and by enthusiasts of alternative history. The Baghdad battery could not have been used for lighting because the voltage and the current it produces are far too small to heat a filament to incandescence or to drive a discharge lamp. The suggestion that the ancient Egyptians used batteries to light the interiors of their tombs, a suggestion that is frequently made in the alternative history literature, and that is based on interpretations of specific Egyptian relief carvings, is not supported by the physical evidence of the Baghdad battery, because the electrical output of the device is many orders of magnitude too small for lighting applications. The Baghdad battery could not have been used for electric shock treatment, at least not in the sense of a deliberate, controlled therapeutic shock, because the current it produces is too small to produce a significant physiological effect on the human body. The tingling sensation that can be produced by touching the electrodes of a Baghdad battery is barely perceptible and is far less intense than the shock produced by a torpedo ray, which was the standard source of therapeutic electrical stimulation in the ancient world. The Baghdad battery could not have been used to power mechanical devices, because the energy it produces is far too small to drive any mechanical apparatus. The suggestion that ancient civilizations used batteries to power advanced devices, a suggestion that is common in the alternative history literature, is not supported by the physical evidence of the Baghdad battery or by any other archaeological evidence. The limitations of the Baghdad battery are important because they constrain the range of plausible interpretations of the artifact's function. The device, if it was used as a battery, could have been used only for applications that require very small amounts of electrical energy, such as electroplating, the production of a mild sensation, or the demonstration of an unusual physical phenomenon. The range of plausible applications is narrow, and the identification of the specific application that the device was used for, if any, requires evidence beyond the physical capability of the device itself. The seventh track of investigation has been the study of the manufacturing techniques that were used to produce the Baghdad battery, aimed at determining whether the construction of the artifact required any special skills or knowledge beyond those available to an ordinary Parthian-era craftsman. The analysis of the manufacturing techniques is important because it bears on the question of whether the artifact was produced by a specialized workshop with access to unusual knowledge, a finding that would support the hypothesis that the artifact was a specialized technological device, or by an ordinary craftsman using standard techniques, a finding that would be consistent with either the battery hypothesis or the alternative hypotheses. The copper cylinder of the Baghdad battery was produced by rolling a sheet of copper into a tube and joining the edges, a technique that was standard in the ancient metalworking tradition, and that did not require any special skills or knowledge. The copper disc that sealed the bottom of the cylinder was soldered or crimped to the tube, again using standard techniques. The iron rod was forged or drawn from a piece of iron using standard ironworking techniques, and the asphalt seal was applied using the standard bitumen working techniques that had been practiced in Mesopotamia for thousands of years. The analysis of the manufacturing techniques therefore indicates that the Baghdad battery was produced using standard, well-known techniques that were available to any competent metalworker in the ancient Near East. The construction of the artifact did not require any special skills or knowledge, and it could have been produced by any workshop that had access to the basic materials, copper, iron, clay, and bitumen, and the basic tools, hammers, anvils, tongs, and furnaces of the metalworking trade. This finding is consistent with both the battery hypothesis and the alternative hypotheses, because both the construction of a battery and the construction of a storage vessel would have required the same basic skills and the same basic materials. The question of the artifact's aesthetic quality is also relevant to the interpretation of its function. The Baghdad battery is not an object of great beauty or great refinement. It is a simple utilitarian object made of common materials and finished without any decorative embellishment. The simplicity of the artifact is more consistent with a practical function, whether that function was the production of electricity or the storage of materials, than with a ceremonial or a prestige function, which would typically be associated with objects of greater artistic quality and greater material value. The question of whether similar artifacts might exist in other museum collections, unrecognized and unstudied, is one that has been raised by researchers who note that the Baghdad battery was identified only because Koenig had the specific knowledge, electrical engineering, needed to recognize the significance of the artifact's configuration. Other artifacts with similar configurations might exist in museum collections around the world, classified as ordinary storage vessels or as unidentified objects, because the curators who catalogued them did not have the specific knowledge needed to recognize their potential significance. The systematic re-examination of Parthian and Sassanid-era artifacts in museum collections, with an eye to identifying objects that might represent galvanic cells or other electrical devices, is a project that has been proposed by several researchers, but that has not yet been systematically undertaken. The eighth track of investigation involves the potential for future archaeological discoveries that could resolve the debate about the Baghdad battery. The Qhapaq Ñan site, where the original artifacts were found, has not been extensively excavated, and the potential for the discovery of additional artifacts, including artifacts that might provide the contextual information needed to determine the function of the battery-like objects, is substantial. The resumption of archaeological excavations at the site under proper scientific conditions and with modern excavation techniques, could potentially produce the evidence that has been missing from the debate for nearly 90 years. The potential for the discovery of similar artifacts at other sites in Iraq and in the broader Near East is also significant. The Parthian and the Sassanid empires controlled vast territories, and the archaeological exploration of these territories is far from complete. The discovery of battery-like artifacts at other sites, particularly if those artifacts were found in clear association with metalworking debris or with electroplated objects, would provide the kind of contextual evidence that is needed to confirm or to refute the battery hypothesis. The political and security conditions in Iraq, which have been disrupted by decades of war and conflict, have severely limited the opportunities for archaeological fieldwork in the country. The resumption of archaeological research in Iraq, which has begun in recent years as security conditions have improved, offers hope that new discoveries may be made that will contribute to the resolution of the Baghdad battery debate and to the broader understanding of the technological capabilities of the ancient Mesopotamian world. The ninth track of investigation has been the study of the historical context of the Baghdad battery's discovery and the evaluation of Koenig's original identification. Koenig's identification of the artifact as a battery has been both praised and criticized by subsequent researchers, and the evaluation of his identification is an important aspect of the scholarly debate. Koenig's background in electrical engineering gave him the specific knowledge that was needed to recognize the arrangement of components in the jar as the components of a galvanic cell, a recognition that would probably not have been made by an archaeologist without engineering training. The identification was therefore a product of Koenig's interdisciplinary expertise, a combination of archaeological and engineering knowledge that allowed him to see the artifact in a way that a specialist in either field alone might not have seen it. The value of interdisciplinary expertise in the interpretation of ancient artifacts is a lesson that the Baghdad battery story has taught the scholarly community, and it has contributed to the growing recognition that the study of ancient technology requires the collaboration of specialists from multiple fields. However, Koenig's identification has also been criticized for being premature and insufficiently supported by evidence. Koenig published his identification before conducting a thorough analysis of the artifact, before examining the archaeological context in which it was found, and before considering the full range of alternative explanations that might account for the artifact's configuration. The criticism is valid because the identification of an ancient artifact as an electrical device is an extraordinary claim that requires extraordinary evidence, and the evidence that Koenig presented, primarily the physical resemblance of the artifact's components to the components of a galvanic cell, was not sufficient to establish the identification beyond reasonable doubt. The debate that has followed Koenig's identification has been productive, in the sense that it has stimulated research, experimentation, and analysis that have deepened our understanding of the artifact and of the technology of the ancient Near East. But the debate has also been frustrating, because it has not produced a definitive answer to the question of the artifact's function, and the prospect of a definitive answer, given the loss of the original artifacts and the incompleteness of the archaeological record, is uncertain. The contribution of the Baghdad battery to the development of the field of archaeometry, the application of scientific methods to the study of archaeological materials, is worth acknowledging. The Baghdad battery has been one of the most discussed artifacts in the history of archaeometry, and the debates that it has generated have contributed to the development of analytical methods, experimental protocols, and interpretive frameworks that have been applied to the study of many other ancient artifacts. The artifact has served as a test case for the application of scientific methods to archaeological problems, and the lessons that have been learned from the study of the Baghdad battery have influenced the broader practice of archaeometry. The question of whether the Baghdad battery will ever be definitively identified as a battery or as something else is one that may depend on factors that are beyond the control of the current generation of researchers. The discovery of new evidence whether from the recovery of the original artifacts, from new excavations at the Kujudet Rabu site, from the analysis of comparable artifacts from other sites, or from the development of new analytical techniques, could potentially resolve the debate. But the discovery of such evidence is not guaranteed, and the possibility that the debate will remain unresolved indefinitely must be accepted as a realistic outcome. The 10th track of investigation involves the broader question of how the Baghdad battery fits into the history of the galvanic cell and the development of electrochemical technology. The modern history of the galvanic cell begins with the experiments of Luigi Galvani in the 1780s, who discovered that the legs of dissected frogs would twitch when contacted with two different metals, a phenomenon that Galvani attributed to animal electricity, an electrical fluid that he believed was generated by the living tissue of the frog. Galvani's experiment stimulated a vigorous debate with Alessandro Volta, who argued that the electrical effect was produced not by the animal tissue, but by the contact between the two dissimilar metals, with the moist tissue serving merely as the electrolyte that completed the circuit. Volta's interpretation of Galvani's experiments led him to construct the voltaic pile in 1800, a device that consisted of alternating discs of copper and zinc separated by discs of cardboard soaked in salt water. The voltaic pile was the first device that could produce a continuous, sustained electrical current, and it was the ancestor of all modern batteries. Volta's invention was a watershed moment in the history of science and technology because it provided the first practical source of electrical energy and because it opened the way for the development of the entire field of electrochemistry, including electrolysis, electroplating, and the electrochemical production of metals and other substances. The Baghdad battery, if it was a battery, would have anticipated Volta's discovery by nearly 2,000 years, demonstrating that the same electrochemical principle that Volta discovered was known and exploited, however imperfectly, in the ancient world. The significance of this anticipation lies not in any suggestion that the ancient discovery influenced the modern one, which it almost certainly did not, but in the demonstration that the electrochemical phenomenon is a natural phenomenon that can be discovered and exploited by any civilization that works with metals and with acidic liquids, regardless of its theoretical understanding of chemistry or physics. The comparison between the Baghdad battery and the voltaic pile reveals both the similarities and the differences between the ancient and the modern devices. Both devices use two dissimilar metals, copper and iron in the Baghdad battery, copper and zinc in the voltaic pile, separated by an electrolyte, to produce an electrical current through an electrochemical reaction. The basic principle is the same. But the voltaic pile was far more sophisticated than the Baghdad battery, both in its design, which stacked multiple cells in series to produce a useful voltage, and in the theoretical understanding that guided its construction. Volta understood, at least in broad terms, the electrochemical principle that his device exploited, and he used this understanding to optimize the design and the performance of the device. The builders of the Baghdad battery, if they understood the electrochemical principle at all, understood it only empirically through the observation of its effects, rather than through the comprehension of its mechanism. The comparison also reveals the importance of the intellectual context in which a technological discovery is made. Volta's discovery was made in the context of the European Enlightenment, a period of intense scientific and philosophical inquiry that provided the intellectual framework within which the discovery could be understood, communicated, and developed. The discovery, if it was made in the Parthian era Near East, was made in a very different intellectual context, one in which the tools for understanding and communicating the electrochemical phenomenon were not available, and in which the discovery, if it was not immediately useful, was likely to be forgotten rather than preserved. The question of whether the Baghdad battery can teach us anything about the modern development of electrochemical technology is one that has been considered by researchers in the field. The answer is that the Baghdad battery, whatever its function, is a reminder that the electrochemical phenomenon is a natural phenomenon that does not require modern science to discover or to exploit, and that the potential for the discovery of new electrochemical phenomena and new electrochemical applications is limited only by the imagination and the curiosity of the people who work with electrochemical systems. The Baghdad battery, if it was a battery, would demonstrate that the first step in the development of a new technology is not the theoretical understanding of the underlying phenomenon, but the empirical observation of the phenomenon itself, an observation that can be made by anyone who has the materials, the opportunity, and the curiosity to investigate the properties of the natural world. The contribution of the Baghdad battery debate to the public understanding of science and of the history of technology has been significant, regardless of the ultimate resolution of the debate. The artifact has brought the history of electrochemistry to the attention of a wide audience, and the debates about its function have provided a vivid and engaging example of the challenges that are involved in the interpretation of ancient technology. The artifact has also stimulated public interest in the broader question of what the ancient world was capable of, a question that has been answered in surprising and humbling ways by the study of other ancient technologies, and that continues to inspire curiosity and investigation. The 11th track of investigation involves the question of what the Baghdad battery tells us about the broader capabilities and the broader intellectual traditions of the Parthian era Near East. The Parthian Empire, which is often overshadowed in the historical literature by its more famous neighbours, the Roman Empire and the Han Dynasty of China, was a civilization of considerable sophistication that made important contributions to the cultural and technological heritage of the ancient world. The Parthian contribution to the history of architecture, which includes the development of the Iwan, the large, barrel-vaulted hall that became one of the most characteristic forms of Islamic architecture, demonstrates the creativity and the technical skill of the Parthian builders. The Parthian contribution to the history of art, which includes the development of a distinctive style of sculpture and relief carving that combined Greek and Persian elements, demonstrates the cultural sophistication of the Parthian court. And the Parthian contribution to the history of commerce, which includes the development and the maintenance of the Silk Road trade network that connected the Roman and the Chinese worlds, demonstrates the organizational capabilities and the commercial acumen of the Parthian state. The Baghdad battery, whatever its function, is a product of this sophisticated and creative civilization, and its existence is a reminder that the Parthian Empire was capable of technological innovation that was not limited to the traditional categories of architecture, art, and commerce. The possibility that the Parthians discovered the electrochemical phenomenon, however imperfectly and however inadvertently, would add another dimension to our understanding of Parthian technological capabilities and would contribute to the rehabilitation of the Parthian Empire as a major player in the history of ancient technology. The comparative study of the technological capabilities of the major ancient civilizations, including the Roman Empire, the Han Dynasty, the Maurya and Gupta empires of India, and the Parthian and Sassanid empires of the Near East, has revealed that each of these civilizations made distinctive contributions to the history of technology that reflected its specific cultural, geographical, and economic characteristics. The Roman contribution was primarily in the areas of construction, infrastructure, and materials technology. The Chinese contribution was primarily in the areas of metallurgy, ceramics, and paper and printing technology. The Indian contribution was primarily in the areas of mathematics, metallurgy, and textile technology. And the Parthian and Sassanid contribution, while it is less well documented than the contributions of the other major civilizations, included significant achievements in architecture, metalwork, and possibly, if the Baghdad battery hypothesis is correct, electrochemistry. The question of why the Parthian technological achievements are less well known than those of the other major ancient civilizations is partly a question of the survival of evidence and partly a question of scholarly attention. The Parthian Empire left fewer monumental structures and fewer written records than the Roman or the Chinese empires, and the archaeological exploration of the Parth heartland in Iraq and Iran has been limited by political instability, military conflict, and the practical difficulties of conducting archaeological research in the region. The relative neglect of Parthian technology in the scholarly literature is therefore partly a consequence of the limitations of the available evidence and partly a consequence of the scholarly bias toward the more extensively documented civilizations of Rome and China. The Baghdad Battery, by virtue of the debate that it has generated and the attention that it has attracted, has done more than any other single artifact to bring the technological capabilities of the Parthian Empire to the attention of the scholarly community and the general public. The artifact has served as a catalyst for research into Parthian technology, Parthian culture, and Parthian history, and it has contributed to a growing recognition that the Parthian Empire was a civilization of considerable technological sophistication that deserves more attention and more study than it has traditionally received. The 12th track of investigation addresses the question of whether the Baghdad Battery could have been used for the production of specific chemical compounds through electrolysis. The electrolysis of various solutions using a copper cathode and an iron anode can produce a range of chemical products depending on the composition of the solution and the conditions of the electrolysis. In a solution containing copper salts, the electrolysis would deposit metallic copper on the cathode, producing a coating of pure copper on whatever object served as the cathode. In a solution containing dissolved iron, the electrolysis would produce iron hydroxide, a compound that could have been used as a pigment or as a medical preparation. The production of chemical compounds through electrolysis is a practical application of the Baghdad Battery that has received less attention than the electroplating hypothesis, but that is equally plausible given the device's electrical output. The production of specific chemical compounds through electrochemical reactions is a well-established modern technology, and the possibility that the ancient users of the Baghdad Battery discovered and exploited this capability, however inadvertently, cannot be ruled out. The investigation of the Baghdad Battery has also contributed to the development of the field of experimental archaeology, the practice of replicating ancient technologies using ancient compatible materials and techniques to understand their capabilities and their limitations. The Baghdad Battery has been one of the most frequently replicated artifacts in the history of experimental archaeology, and the experiments that have been conducted on it have established important methodological principles for the replication and the testing of ancient technological devices. The principle that the replication must use only materials and techniques that were available to the ancient practitioners, the principle that the performance of the replica must be measured using quantitative methods, and the principle that the results must be compared with the physical evidence of the original artifact are all principles that have been reinforced and refined through the experimental study of the Baghdad Battery. The question of whether future technological developments might provide new tools for the investigation of the Baghdad Battery is one that gives hope for the eventual resolution of the debate. The development of new analytical techniques, including more sensitive methods for detecting chemical residues, more precise methods for characterizing corrosion products, and more powerful computational methods for modeling electrochemical processes, could potentially provide new evidence that would tip the balance of the debate toward one interpretation or another. The development of new archaeological techniques, including improved methods for surveying and excavating ancient sites, could potentially lead to the discovery of new artifacts or new contextual information that would illuminate the function of the Baghdad Battery and the stabilization of the political situation in Iraq, which would allow the resumption of systematic archaeological research in the region, could potentially lead to the excavation of additional sites where Baghdad Battery-type artifacts might be found in clear, well-documented contexts. The Baghdad Battery remains, after nearly 90 years of study, one of the most enigmatic and one of the most provocative artifacts in the history of archaeology. The debate about its function has not been resolved, and the resolution, if it comes, may come from a direction that no one has anticipated. the artifact continues to fascinate, to provoke, and to challenge, reminding us that the ancient world was a place of greater complexity and greater capability than we sometimes imagine, and that the artifacts it has left behind can still surprise us with their implications and their mysteries. Everything we have discussed so far concerns the specific physical properties of the Baghdad battery, the specific hypotheses that have been proposed for its function, and the specific evidence that supports or undermines each hypothesis. These are important matters, and the debate about the Baghdad battery continues to generate new research and new arguments. But beneath the specific details of the debate lies a deeper truth, a truth that concerns not just what the Baghdad battery was, but what it represents, what it tells us about the nature of technological discovery, and what it implies about the relationship between knowledge and the historical record. The deeper truth is this: the Baghdad battery is a reminder that the historical record is incomplete, that the surviving evidence of ancient technology represents only a fraction of what once existed, and that the technologies that the ancient world possessed may have been more diverse and more sophisticated than the evidence allows us to confirm. Whether the Baghdad battery is a battery or a scroll jar or a medical device, its existence demonstrates that the ancient world produced objects whose function is not immediately apparent from their physical form, objects that challenge our assumptions about what the ancients were capable of, and that remind us that the absence of evidence is not evidence of absence. This is not science fiction. This is a fundamental principle of archaeological interpretation, a principle that is often stated, but that is easily forgotten in the rush to classify and to categorize the artifacts of the ancient world. The objects that have survived from the ancient world are a biased sample, biased toward objects that are made of durable materials, that were deposited in environments that favored preservation, and that were produced in quantities large enough to ensure that at least some examples would survive. The objects that have not survived, objects made of wood, leather, cloth, and other perishable materials, objects that were produced in small quantities or that were deposited in environments that did not favor preservation, are invisible to the archaeological record, and the technologies and the practices that they represent are invisible as well. The Baghdad battery may represent one such invisible technology, a technology that was known in the ancient world, but that left so little physical evidence that its existence can only be inferred, not confirmed. The electrochemical phenomenon that the Baghdad battery may have exploited is a phenomenon that can be produced with common materials, copper, iron, and an acidic liquid that would have been available to any metalworker in the ancient Near East. The discovery of this phenomenon, through the accidental immersion of iron and copper in an acidic solution and the observation of a tingling sensation or a slight warming, would not have required any theoretical knowledge of chemistry or physics. It would have required only the empirical observation that a specific combination of common materials produced a specific unusual effect. Something is wrong with our assumptions about how technological discoveries are made and how they are preserved. We tend to assume that significant technological discoveries are always documented, always preserved in the historical record, and always transmitted to subsequent generations. The history of technology, however, is full of examples of discoveries that were made and then lost, technologies that were developed and then forgotten, capabilities that existed for a time and then disappeared. The Baghdad battery, whether it was a battery or not, is a reminder that the process of technological discovery is not always accompanied by the process of technological preservation, and that discoveries can be made and lost without leaving any trace in the historical record. The concept of independent discovery, the phenomenon in which the same technology or the same principle is discovered independently by different people in different places at different times, is relevant to the Baghdad battery debate. The history of technology includes numerous examples of independent discovery in which the same invention was made independently by different inventors who had no knowledge of each other's work. The development of agriculture, which occurred independently in at least 6 different parts of the world. The development of writing, which occurred independently in at least 3 or 4 different regions. and the development of metallurgy, which occurred independently in multiple regions, are all examples of independent discovery that demonstrate that similar environmental and cultural conditions can produce similar technological outcomes. If the Baghdad battery represents a discovery of the electrochemical phenomenon, this discovery would have been an example of independent discovery, a discovery of the same phenomenon that Volta would discover independently nearly 2,000 years later. The electrochemical phenomenon is a natural phenomenon that arises whenever two different metals are placed in contact with an acidic or alkaline solution, and the discovery of this phenomenon by the ancient Mesopotamians, if it occurred, would not require any special genius or any knowledge that was not available to the ancient metalworkers. The phenomenon is, in a sense, waiting to be discovered by anyone who works with metals and with acidic liquids, and the surprise would not be that the ancients discovered it, but that we have so little evidence that they did. The relationship between the Baghdad battery and the broader history of lost technologies that we have explored in this series provides a framework for understanding the artifact's significance. The Antikythera mechanism, which demonstrated that the ancient Greeks were capable of building precision-geared computers. Damascus steel, which demonstrated that the ancient metalworkers were capable of producing nanostructured materials. Greek fire, whose formula was lost with the Byzantine Empire. Roman concrete, which is stronger and more durable than modern Portland cement. The Lycurgus cup, which demonstrated that the Romans practiced nanotechnology. Each of these lost technologies challenges the modern assumption of technological superiority and demonstrates that the ancient world was capable of achievements that the modern world has struggled to understand, let alone to replicate. The Baghdad battery fits into this pattern, though with an important difference. The other lost technologies that we have discussed are confirmed technologies, objects whose function is known and whose properties have been verified by scientific analysis. The Baghdad battery is an unconfirmed technology, an object whose function is debated and whose properties are consistent with multiple interpretations. The Baghdad battery is therefore not a proof of ancient electrical technology in the same way that the Antikythera mechanism is a proof of ancient mechanical computing. It is, instead, a possibility, a tantalizing suggestion that the ancient world may have discovered a phenomenon that we consider to be modern, a suggestion that cannot be confirmed or denied with the evidence currently available. The ambiguity of the Baghdad battery is itself instructive, because it illustrates the limits of what archaeological evidence can tell us about the technologies of the past. The physical evidence of an artifact can tell us what the object is made of, how it was constructed, and what it is capable of doing. But it cannot, by itself, tell us what the object was used for, because the function of an object is determined by the intention of its maker and the practice of its user, information that is not preserved in the physical properties of the object itself. The function must be inferred from the context, from the association with other objects and with other evidence that indicates how the object was used in the cultural system that produced it. When the context is lost, as it has been for the Baghdad battery, the function becomes a matter of inference and speculation rather than of knowledge. Let that sink in. The Baghdad battery may be one of the most important technological artifacts ever recovered from the ancient world, or it may be a misidentified storage vessel. The difference between these two interpretations is not a difference in the physical evidence, which is the same in both cases, but a difference in the interpretation of that evidence, which depends on contextual information that has been lost. The lesson of the Baghdad battery is that the recovery and the preservation of archaeological context, the specific information about where an object was found, what it was found with, and how it was deposited, is as important as the recovery of the object itself, because it is the context that transforms an object into evidence, and that allows the object to tell us something about the people who made it and the world in which they lived. Let that sink in once more. The physical evidence is the same. The interpretations are radically different, and the information that would resolve the ambiguity, the archaeological context, has been lost, partly through inadequate documentation and partly through the devastation of war and looting. The Baghdad Battery is a cautionary tale about the importance of context in archaeological interpretation, and about the consequences of losing that context through negligence or through violence. The question of whether the ancient world possessed electrical technology is one that the Baghdad Battery raises, but does not answer. The artifact provides a tantalizing suggestion of ancient electrical knowledge, but it does not provide proof, and the debate about its function is likely to continue for as long as the evidence remains ambiguous. The debate is valuable, however, because it keeps alive the question of what the ancient world was capable of, a question that has been answered in surprising and humbling ways by the study of other ancient technologies, and that may yet be answered in equally surprising ways by the study of the Baghdad Battery and of the other enigmatic artifacts that the ancient world has left behind. The relationship between the Baghdad Battery and the philosophy of science provides a useful framework for understanding the epistemological challenges that the artifact presents. The philosophy of science, which studies the nature and the limits of scientific knowledge, has developed a number of concepts that are relevant to the Baghdad Battery debate, including the concept of underdetermination, the concept of inference to the best explanation, and the concept of the relationship between evidence and theory. The concept of underdetermination, which refers to the situation in which the available evidence is consistent with multiple mutually exclusive theories, is directly applicable to the Baghdad Battery. The physical evidence of the artifact is consistent with the battery hypothesis, the scroll storage hypothesis, the medical hypothesis, and the simple storage hypothesis, and the evidence does not decisively favour any one of these hypotheses over the others. The debate about the Baghdad Battery is therefore a case of underdetermination, a situation in which the evidence is insufficient to determine the correct interpretation. The concept of inference to the best explanation, which refers to the process of selecting the hypothesis that provides the most satisfying explanation of the available evidence, provides a framework for evaluating the competing hypotheses. Each hypothesis explains some features of the artifact better than others. The battery hypothesis explains the specific arrangement of components and the insulation of the iron from the copper. The scroll storage hypothesis explains the general form of the artifact and the use of copper as a protective container. The medical hypothesis explains the electrical capability of the device and its consistency with known medical practices, and the simple storage hypothesis explains the overall form of the artifact with the fewest assumptions. The selection of the best explanation depends on the criteria that are used to evaluate the hypotheses, and different researchers, applying different criteria, have arrived at different conclusions. The concept of the burden of proof is also relevant to the debate. The battery hypothesis, which proposes that the ancient Mesopotamians possessed a knowledge of electricity that is not documented in any surviving written source, and that is not attested by any other archaeological evidence, bears a heavier burden of proof than the alternative hypotheses, which propose functions for the artifact that are consistent with known ancient practices and that do not require the assumption of extraordinary capabilities. The principle of parsimony, which favours the simplest explanation that is consistent with the evidence, tends to favour the alternative hypotheses over the battery hypothesis, because the alternative hypotheses require fewer assumptions and invoke fewer capabilities that are not otherwise attested. The application of Bayesian reasoning to the Baghdad Battery debate provides a formal framework for evaluating the competing hypotheses. Bayesian's reasoning involves the assessment of the prior probability of each hypothesis, the likelihood of the evidence given each hypothesis, and the posterior probability of each hypothesis given the evidence. The prior probability of the battery hypothesis is low because the existence of ancient electrical technology is not supported by other evidence, while the prior probability of the scroll storage or simple storage hypotheses is higher, because these functions are well attested in the ancient Near East. The likelihood of the evidence given the battery hypothesis is moderate, because the specific arrangement of components is more consistent with the battery hypothesis than with the alternatives, but the likelihood given the alternatives is also substantial. The posterior probability of the battery hypothesis, while it is higher than the prior probability, is still relatively low, reflecting the strength of the prior against the evidence. The broader implications of the Baghdad battery for the history of electrochemistry are worth exploring in detail. The modern history of electrochemistry is typically traced from the experiments of Luigi Galvani in the 1780s, who discovered that the contact of two different metals with the nerve of a frog's leg produced a muscular contraction, through the work of Alessandro Volta, who built the first true battery in 1800, to the development of modern electrochemical technology, which encompasses batteries, fuel cells, electrolysis, and a wide range of other applications. The standard narrative presents the discovery of electrochemistry as a product of the European Enlightenment, a period of intellectual ferment that produced a series of fundamental scientific discoveries that transformed the understanding of the natural world. The Baghdad battery challenges this standard narrative by suggesting that the electrochemical phenomenon may have been discovered, whether deliberately or accidentally, nearly 2,000 years before Galvani and Volta. If the Baghdad battery is a galvanic cell, the discovery of the electrochemical phenomenon would be a discovery of the ancient world rather than a discovery of the Enlightenment, and the standard narrative of the history of electrochemistry would need to be revised to accommodate the possibility that the phenomenon was known in the ancient Near East. The revision of the standard narrative would not diminish the significance of Galvani's and Volta's contributions, which were based on systematic experimental investigations, and on a theoretical understanding of the underlying phenomena that was far more advanced than anything that was available to the ancient Mesopotamians, but it would demonstrate that the basic phenomenon, the production of an electrical current by the contact of dissimilar metals with an electrolyte, is a natural phenomenon that can be discovered by anyone who works with the appropriate materials, and that the discovery of this phenomenon does not require the specific intellectual conditions of the European Enlightenment. The history of science includes numerous examples of phenomena that were observed in the ancient world, but that were not understood or formally described until the modern era. The phenomenon of magnetism, for example, was observed by the ancient Greeks, who noticed the attractive properties of lodestone, a naturally magnetized mineral, but it was not formally described or explained until the work of William Gilbert in the 16th century and the subsequent development of electromagnetic theory. The phenomenon of refraction, which is the bending of light as it passes through a medium of different density, was observed by the ancient Egyptians, who used lenses for magnification, but it was not formally described until the work of Willibrord Snellius in the 17th century. The Baghdad battery, if it is a battery, would be another example of a natural phenomenon that was observed and exploited in the ancient world, but that was not formally understood until the modern era. The concept of anticipatory technology, technology that anticipates later developments without being connected to them, is useful for understanding the significance of the Baghdad battery in the history of electrochemistry. The Baghdad battery, if it is a battery, would be an anticipatory technology, a device that embodied the same electrochemical principle as the modern battery, but that was not connected, as far as is known, to the later development of electrochemical technology by Galvani and Volta. The existence of anticipatory technologies demonstrates that the same natural phenomena can be discovered and exploited independently by different people at different times, and that the trajectory of technological development is not a single, continuous line, but a complex, branching network of independent discoveries, some of which are connected to subsequent developments, and some of which are dead ends that are not followed up by later innovators. The educational value of the Baghdad battery as a teaching tool in the history of science and in the philosophy of technology is considerable. The artifact provides a compelling case study in the interpretation of ambiguous evidence, in the relationship between capability and intention, and in the limits of what archaeological evidence can tell us about the technologies of the past. The debate about the Baghdad battery which involves arguments from physics, chemistry, archaeology, history, and philosophy, provides an excellent example of the interdisciplinary nature of the study of ancient technology and of the challenges that arise when evidence from different disciplines must be integrated into a coherent interpretation. The Baghdad Battery also raises important questions about the nature of technological discovery itself. The standard model of technological discovery, which presents the process as a deliberate, goal-directed activity in which inventors consciously set out to solve specific problems and develop specific solutions, is only one model of how technology is developed. The alternative model of accidental discovery, in which technologies are discovered inadvertently through the exploration of natural phenomena or through the pursuit of unrelated goals, is equally well supported by the historical evidence, and may account for many of the most important technological innovations in human history. The discovery of the electrochemical phenomenon, if it occurred in ancient Mesopotamia, would almost certainly have been an accidental discovery rather than a deliberate invention. The ancient metalworkers who might have discovered the phenomenon would not have set out to build a battery or to generate an electrical current. They would have been engaged in their ordinary work, immersing metals in acidic solutions for cleaning, for etching, or for other standard metalworking purposes, and they would have noticed the unusual effects, the tingling sensation, the warming, the corrosion of the metal that occurred when dissimilar metals were placed in contact with the same solution. The observation of these effects and the curiosity to investigate them further would have been the first steps in the development of the technology that the Baghdad Battery may represent. The role of curiosity in technological discovery is a theme that connects the Baghdad Battery to the broader history of human innovation. The discovery of new technologies is driven not only by the practical need for new tools and new capabilities, but also by the basic human curiosity about the properties of the natural world. The ancient craftsman who first noticed the tingling sensation produced by the contact of copper and iron in an acidic solution was driven not by a need for electricity, which he could not have imagined, but by a curiosity about the unusual phenomenon he had observed. The investigation of that phenomenon, motivated by curiosity rather than by practical need, would have been the first step in the development of a technology whose potential applications the discoverer could not have foreseen. The parallel with other accidental technological discoveries is instructive. The discovery of penicillin by Alexander Fleming, which occurred when Fleming noticed that a mold that had contaminated one of his bacterial cultures was killing the bacteria, was an accidental discovery that was driven by the observation of an unexpected phenomenon and by the curiosity to investigate it further. The discovery of X-rays by Wilhelm Röntgen, which occurred when Röntgen noticed that a fluorescent screen in his laboratory was glowing in response to radiation from a cathode ray tube, was another accidental discovery that was driven by observation and curiosity. The Baghdad Battery, if it represents an ancient discovery of the electrochemical phenomenon, would be another example of the same pattern, an accidental observation followed by an investigation driven by curiosity that led to the development of a new technology. The vulnerability of accidental discoveries to loss is a corollary of their accidental nature. A technology that is discovered accidentally through the observation of an unexpected phenomenon is more likely to be lost than a technology that is developed deliberately through a systematic research program, because the accidental discovery is less likely to be documented, less likely to be understood in terms of its underlying principles, and less likely to be integrated into the broader body of technological knowledge. The Baghdad Battery, if it represents an accidental discovery of the electrochemical phenomenon, would be consistent with this pattern, a discovery that was made, that was used for some specific purpose, and that was then lost because the discovery was not documented, not understood, and not transmitted to subsequent generations. The concept of the discovery horizon, the boundary between what a civilization has discovered and what it has not, is useful for understanding the significance of the Baghdad Battery. The discovery horizon of the Parthian-era Mesopotamians included writing, mathematics, astronomy, metallurgy, and many other fundamental technologies that had been developed over millennia of continuous civilization. The question of whether the discovery horizon also included the electrochemical phenomenon is the question that the Baghdad battery raises, and the answer to that question, if it is ever determined, will have important implications for our understanding of the scope and the limits of ancient knowledge. The question of what would constitute definitive proof that the Baghdad battery was used as a battery is one that deserves careful consideration, because the standards of evidence that are required to confirm the battery hypothesis are higher than the standards that would be required to confirm a more conventional interpretation. The identification of an ancient artifact as an electrical device is an extraordinary claim, and extraordinary claims require extraordinary evidence. The physical evidence of the Baghdad battery, while it is consistent with the battery hypothesis, is also consistent with alternative hypotheses, and the evidence does not meet the standard of extraordinary proof that is required to establish the battery hypothesis beyond reasonable doubt. The types of evidence that would constitute definitive proof of the battery hypothesis include the discovery of electroplated objects at the same archaeological site, with coatings that exhibit the specific microstructural features that distinguish electroplated coatings from coatings applied by other techniques. The discovery of wires, connectors, or other electrical components that would indicate the existence of a circuit into which the battery was connected. The discovery of textual references in Pantheon or Sassanid-era sources that describe the use of an electrical device or the observation of an electrochemical phenomenon, and the identification of specific chemical residues inside the copper cylinder that are consistent with the use of an acidic electrolyte and that are inconsistent with the alternative hypotheses. None of these types of evidence has been found, and the prospect of finding them is uncertain. The incomplete excavation of the Qujut Rabu site means that additional evidence might exist at the site but has not yet been recovered. The loss of the original artifact during the looting of the Baghdad Museum means that the chemical analysis of the residues inside the copper cylinder can no longer be performed on the original objects, and the absence of textual references to electrical technology in the surviving Parthian and Sassanid-era sources means that the confirmation of the battery hypothesis from the literary record is unlikely. The situation is therefore one of permanent or near-permanent ambiguity, in which the battery hypothesis can neither be confirmed nor definitively refuted with the evidence currently available. This situation is frustrating for researchers who would prefer a definitive answer, but it is not unusual in the study of ancient technology, where the evidence is often fragmentary and where the interpretation of the evidence often depends on assumptions and inferences that cannot be independently verified. The acceptance of ambiguity is itself a form of intellectual honesty, a recognition that the evidence sometimes does not provide a clear answer, and that the imposition of a definitive interpretation on ambiguous evidence is a form of intellectual dishonesty that does a disservice to the evidence, to the artifact, and to the people who produced it. The Baghdad battery deserves an honest assessment, one that acknowledges the strengths and the weaknesses of all the competing hypotheses, and that resists the temptation to claim certainty where certainty is not warranted. The value of the Baghdad battery as a subject of ongoing research and debate lies not in the prospect of a definitive answer, but in the quality of the questions that the artifact raises, and in the insights that the investigation of those questions has produced. The research on the Baghdad battery has advanced our understanding of ancient metallurgy, of ancient chemical practices, of the archaeology of the Parthian and Sassanid periods, and of the broader history of electrochemical technology. These advances have value regardless of whether the battery hypothesis is ultimately confirmed or refuted, and they justify the continued investigation of the artifact and of the questions that it raises. The question of whether the knowledge represented by the Baghdad battery, if it was a battery, was transmitted beyond the boundaries of the Parthian Empire, is one that has been explored by researchers who have investigated the trade and the cultural connections between the Parthian world and the other major civilizations of the ancient world. The Parthian Empire was connected to the Roman Empire to the west, to the Kushan Empire and the Indian subcontinent to the east, and to the Chinese Han Dynasty through the Silk Road trade network. The possibility that knowledge of the electrochemical phenomenon, if it was discovered in the Parthian Near East, might have been transmitted along these trade routes to other parts of the ancient world is one that cannot be ruled out, though no evidence of such transmission has been identified. The absence of evidence for the transmission of electrochemical knowledge to other ancient civilizations is consistent with the hypothesis that the knowledge, if it existed, was localized and was not widely shared. The electrochemical phenomenon, while it is easily observable, is not easily understood without a theoretical framework, and the practical applications of the phenomenon, as we have discussed, are limited and not obviously useful. The knowledge of the phenomenon might therefore have been confined to a small group of practitioners, perhaps a single workshop or a single community, who used it for a specific, limited purpose and who did not attempt to disseminate the knowledge more widely. The parallel with other examples of localized technological knowledge is instructive. The knowledge of how to produce Damascus steel was confined to a specific community of metalworkers in South Asia and the Middle East. The knowledge of how to produce Greek fire was confined to the Byzantine Empire. The knowledge of how to produce the dichroic glass of the Lycurgus cup was confined to a small number of Roman glassmakers. In each of these cases, a significant technological achievement was confined to a limited geographical area and a limited group of practitioners, and the knowledge was eventually lost when the conditions that sustained it changed. The Baghdad battery, if it represents a similar localized technological achievement, would fit the same pattern of local innovation, limited dissemination, and eventual loss. What does the Baghdad battery mean for our understanding of the relationship between ancient technology, archaeological evidence, and the limits of historical knowledge? What does it tell us about the process of technological discovery, the preservation of technological knowledge, and the role of evidence in the interpretation of the past? The first implication is a recognition of the fundamental uncertainty that characterizes the study of ancient technology. The Baghdad battery illustrates, more clearly than almost any other artifact, the gap between what we can observe and what we can know, between the physical evidence that survives from the ancient world and the interpretation that we impose upon it. The physical evidence of the Baghdad battery is unambiguous: a clay jar, a copper cylinder, an iron rod, a bitumen seal. The interpretation of this evidence is deeply ambiguous: a battery, a scroll jar, a medical device, a storage vessel. The gap between the evidence and the interpretation is a gap that can be narrowed but not closed by further analysis, because the information that would close it, the archaeological context, the literary references, the testimony of the makers and the users, has been irretrievably lost. The second implication is a recognition of the importance of preserving archaeological context, the specific information about the location, the associations, and the circumstances of an artifact's discovery that transforms the artifact from a physical object into a piece of historical evidence. The loss of the Baghdad battery's archaeological context through incomplete excavation records and through the destruction of war and looting has made it impossible to determine the artifact's function with certainty, and it has condemned the scholarly debate about the artifact to a state of permanent ambiguity. The lesson for the modern world is that the protection of archaeological sites and the meticulous documentation of archaeological excavations are essential for the preservation of the information that gives meaning to the objects that are recovered from the ground. There is a pause worth taking here. Consider all of the artifacts that are sitting in museum basements around the world, objects that were recovered from archaeological sites decades or centuries ago, and that have never been fully studied or fully understood. Consider the objects that were excavated without proper documentation, without photographs, without detailed records of their specific locations and their specific associations. Consider the information that was lost when these objects were removed from their context. Information that can never be recovered, no matter how sophisticated the analytical techniques that are applied to the objects themselves. The Baghdad battery is not the only artifact whose interpretation has been compromised by the loss of context. It is simply the most famous. The third implication is a recognition of the role that modern technology plays in the interpretation of ancient artifacts. The Baghdad battery was identified as a potential electrical device by Wilhelm Koenig, an archaeologist who had studied electrical engineering, because he possessed the specific knowledge that was needed to recognize the arrangement of components inside the jar as the components of a galvanic cell. Without Koenig's training in electrical engineering, the artifact might have been catalogued as an ordinary storage vessel and forgotten, its potential significance unrecognized. The discovery of the Baghdad battery's potential as an electrical device was therefore the result of the application of modern knowledge to an ancient artifact, a process that has been repeated in the study of many other ancient technologies, and that demonstrates the importance of interdisciplinary expertise in the interpretation of the archaeological record. The fourth implication concerns the ethics of sensationalism in the interpretation of ancient artifacts. The Baghdad battery has been a favorite of alternative history writers and television producers, who have often presented the battery hypothesis as though it were established fact rather than an unproven hypothesis. The sensationalized treatment of the Baghdad battery has contributed to a public perception that the ancient world was far more technologically advanced than the scholarly consensus supports, a perception that, while it is not entirely wrong, is based on an incomplete and often misleading presentation of the evidence. The responsibility of scholars and of science communicators to present the evidence accurately and to acknowledge the uncertainty that characterizes the interpretation of enigmatic artifacts like Baghdad battery is an important ethical obligation that is not always fulfilled. The broader question of what we owe to the artifacts of the past, the question of how we should treat the objects that the ancient world has left behind, is one that the Baghdad battery raises in a particularly poignant way. The artifacts of the ancient world are the only physical evidence we have of the technologies, the practices, and the beliefs of the people who lived before us. They are the only witnesses to a past that can no longer speak for itself. The treatment of these artifacts, whether they are studied with care and respect, or neglected and damaged and destroyed, determines the quality and the completeness of the evidence that is available to us, and it determines, in a very real sense, the extent of our knowledge of the past. The destruction of the National Museum of Iraq in 2003, which resulted in the loss or the damage of thousands of artifacts, including some of the Baghdad battery artifacts, was a catastrophe not only for Iraqi cultural heritage, but for the global understanding of ancient Mesopotamian technology. The loss of these artifacts is a loss that can never be recovered, because the physical evidence that they contained, the specific chemical compositions, the specific microstructural features, the specific residues and traces that might have resolved the debate about their function, is gone forever. The destruction of the Baghdad Museum is a reminder that the preservation of cultural heritage is not merely an academic concern. It is a moral obligation, a responsibility that the modern world owes to the past and to the future, a responsibility that in the case of the Baghdad battery was not fulfilled. The relationship between the Baghdad battery and the concept of technological precursors, technologies that anticipated later developments without being directly connected to them, provides a useful perspective on the artifact's significance. The history of technology includes many examples of technological precursors, inventions that embodied the principles of later, more successful technologies, but that were not developed or exploited to their full potential. The eolipile, a steam-powered spinning device described by Hero of Alexandria in the 1st century of the Common Era, is often cited as a precursor of the steam engine, though the eolipile was not developed into a practical power source, and was not connected, as far as is known, to the development of the steam engine in the 18th century. The Baghdad battery, if it was a battery, would be a technological precursor of the modern galvanic cell, embodying the same electrochemical principle that Volta would independently discover nearly 2 millennia later. The significance of the Baghdad battery as a technological precursor would lie not in any direct connection between the ancient and the modern technologies, which is not attested by any evidence, but in the demonstration that the same natural phenomenon was recognized and exploited by different people at different times in different parts of the world. The concept of technological precursors is important because it challenges the linear narrative of technological progress that is often presented in the history of science and technology. The linear narrative presents the history of technology as a continuous, progressive development in which each generation builds upon the achievements of the previous generation and in which the trajectory of development is always forward. The existence of technological precursors, which demonstrate that specific technologies were discovered and then lost before being rediscovered, challenges this narrative and suggests that the history of technology is more complex, more contingent, and more cyclical than the linear narrative implies. The Baghdad battery, whether it is a battery or not, enriches our understanding of the technological capabilities and the intellectual traditions of the ancient Near East, and it reminds us that the ancient world was a place of far greater technological sophistication and far greater intellectual curiosity than the popular imagination often credits. The artifact is a testament to the ingenuity of the people who made it, regardless of its function, and it is a reminder that the study of the ancient world can still produce surprises that challenge our assumptions and expand our understanding of what the human mind and the human hand are capable of achieving. The fifth implication of the Baghdad battery concerns the relationship between skepticisms and open-mindedness in the interpretation of ancient technology. The scholarly response to the Baghdad battery illustrates the tension between the obligation to evaluate evidence critically and the obligation to remain open to the possibility that the evidence may support conclusions that are unexpected or that challenge established assumptions. The skeptics, who point to the weakness of the contextual evidence and to the availability of alternative explanations, are fulfilling the scholarly obligation of critical evaluation. The proponents, who point to the physical evidence and to the experimental confirmation that the artifact can produce electricity, are fulfilling the scholarly obligation of open-mindedness. The ideal scholarly position, which combines critical evaluation with open-mindedness, is one that acknowledges the strengths and the weaknesses of both the battery hypothesis and the alternative hypotheses, that recognizes the fundamental uncertainty that characterizes the interpretation of the artifact, and that remains open to the possibility that new evidence, whether from further analysis of the existing artifacts, from new archaeological discoveries, or from the development of new analytical techniques, may eventually resolve the debate. The scholarly community has, for the most part, maintained this balanced position, though individual scholars have occasionally strayed toward one extreme or the other. The public discourse about the Baghdad battery, which has been conducted primarily in popular books, television documentaries, and on the internet, has been less balanced than the scholarly discourse. The popular treatment of the Baghdad battery has tended to favor the battery hypothesis, because it is more dramatic and more attention-grabbing than the alternative hypotheses, and it has often presented the hypothesis as though it were established fact rather than an unproven interpretation. The discrepancy between the popular and the scholarly treatments of the Baghdad battery is a source of frustration for scholars who have seen their careful, nuanced analyses oversimplified and distorted in the popular media. The responsibility for addressing this discrepancy falls on both the scholarly community and the media. The scholarly community has a responsibility to communicate its findings clearly and accessibly to the public, making the complexity and the uncertainty of the evidence as vivid and as compelling as the dramatic but oversimplified narratives of the popular media. The media has a responsibility to present the evidence accurately and to acknowledge the uncertainty that characterizes the interpretation of enigmatic artifacts like the Baghdad battery. The fulfillment of these responsibilities would contribute to a more informed and more nuanced public understanding of the Baghdad battery and of the broader questions about ancient technology that it raises. The sixth implication of the Baghdad battery concerns the relationship between artifact and context in archaeological interpretation. The Baghdad Battery is a case study in the importance of archaeological context, the specific information about where an artifact was found, what it was found with, and how it was deposited for determining the function and the significance of the artifact. The loss of the Baghdad Battery's archaeological context has made it impossible to determine the artifact's function with certainty, and the lesson that the artifact teaches is that the recovery of an artifact without the recovery of its context is only half the job of archaeology, and it is the less important half. The importance of context in archaeological interpretation cannot be overstated. An artifact without context is an object without meaning, a physical form without a function, a product without a process. The context provides the information that transforms the artifact from a physical object into a piece of evidence, information about the social, economic, and cultural practices that produce the artifact and that gave it its function and its meaning. The loss of context, whether through inadequate excavation, through the destruction of sites by development or by conflict, or through the looting of sites by treasure hunters, is a permanent loss that cannot be compensated for by any amount of subsequent analysis of the artifact itself. The Baghdad Battery is a powerful example of this principle, because the loss of its context has condemned the debate about its function to a state of permanent ambiguity that could have been resolved if the context had been properly recorded and preserved. The lesson of the Baghdad Battery for the modern archaeological community is that the investment in proper excavation methods, in detailed documentation, and in the preservation of contextual information is not merely a methodological best practice, it is an ethical obligation, a responsibility that the archaeological community owes to the artifacts that it recovers and to the future researchers who will study them. The clay jar sits in its display case, or perhaps it does not. Perhaps it was stolen, perhaps it was broken, perhaps it is sitting in a warehouse or a private collection, waiting to be rediscovered and studied. The uncertainty about the fate of the original Baghdad Battery artifacts mirrors the uncertainty about their function, a double ambiguity that leaves the researcher with questions that may never be answered, and with possibilities that may never be confirmed. What we know is this: in the Parthian period, in the ancient land of Mesopotamia, someone made a clay jar and placed inside it a copper cylinder and an iron rod sealed with bitumen. The arrangement of these components is consistent with the design of a galvanic cell, a device that converts chemical energy into electrical energy. If the jar was filled with an acidic liquid, it would have produced a small but measurable electrical current, a current that could have been used for electroplating, for medical or ritual purposes, or for some other application that we have not yet imagined. We do not know why the jar was made. We do not know what it was used for. We do not know whether the people who made it understood the electrochemical phenomenon that the arrangement of components in the jar could produce. We do not know whether they used the electrical current for any practical purpose. We do not know whether the Baghdad Battery was a battery at all. What we do know is that the artifact is extraordinary regardless of its function. It is extraordinary because it demonstrates the inventiveness and the sophistication of the ancient Mesopotamian metalworkers, who produced an object that, whether or not it was intended as a battery, is capable of producing a phenomenon that was not formally identified by modern science until the late 18th century. It is extraordinary because it has provoked nearly a century of debate among scholars, scientists, and enthusiasts, a debate that has enriched our understanding of ancient technology and that has challenged our assumptions about the limits of ancient knowledge. And it is extraordinary because it remains, after all these years of study, a mystery, an object whose function cannot be determined with certainty and whose significance cannot be fully assessed. The Baghdad Battery is a test of intellectual humility. It is a test of our willingness to say, "We do not know," to resist the temptation to impose a definitive interpretation on ambiguous evidence, to accept that the past contains mysteries that may never be solved. The battery hypothesis is seductive because it is dramatic and because it overturns our comfortable assumptions about the trajectory of technological progress. The storage hypothesis is cautious because it is consistent with the known practices of the ancient world and because it does not require the assumption of capabilities that are not documented in any surviving source. The truth may lie with either hypothesis or with neither, or somewhere in between. The ancient Mesopotamians, whoever they were and whatever they intended, left behind a small clay jar that has provoked more discussion, more debate, and more fascination than objects, 1,000 times its size and 1,000 times its cost. The jar is a testament to the enduring power of a good question, a question that does not have a clear answer, but that stimulates the imagination and that challenges the assumptions of those who ask it. The question of the Baghdad Battery is such a question, and it is a question that deserves to be asked again and again, for as long as there are people who are curious about what the ancient world knew and what it could do. The jar is small, the mystery is large. The answer remains hidden, somewhere in the gap between what we can see and what we can know, between the evidence that survives and the context that is lost, between the artifact that endures and the knowledge that has vanished. The Baghdad Battery waits, as it has waited for 2,000 years, for someone to discover its secret, whether that discovery will confirm the battery hypothesis or refute it, whether it will reveal an ancient knowledge of electricity or merely an ancient technique for storing scrolls. It will, when it comes, add another chapter to the story of human ingenuity, a story that stretches back to the first tool and that reaches forward to the last question that a human mind will ever ask. The jar is silent, the copper is green with age, the iron has corroded to rust, but the question it poses is still alive, still burning, still demanding an answer. And the answer, if it comes, will tell us something not only about a small clay jar from ancient Mesopotamia, but about the nature of human curiosity, about the limits of human knowledge, and about the extraordinary things that can be accomplished by ordinary materials in the hands of people who were, in ways that we are only beginning to understand, not so different from ourselves. The story of the Baghdad Battery is ultimately a story about the limits of knowledge, about the boundary between what we can determine and what we cannot, about the gap between the evidence that survives and the interpretation that we seek. The artifact sits at this boundary, illuminated from one side by the evidence of its physical form, and from the other side by the darkness of its lost context, visible enough to provoke questions, but not clear enough to provide answers. The debate about the Baghdad Battery will continue, as it has continued for nearly 90 years, because the evidence that would resolve it is missing, and because the questions that it raises are too important and too fascinating to be abandoned. The debate is not merely about a small clay jar from ancient Mesopotamia. It is about the nature of technological discovery, about the relationship between capability and intention, about the permanence of knowledge and the fragility of evidence, and about the capacity of the ancient world to surprise us with achievements that we did not expect and that we cannot fully explain. The researchers who study the Baghdad Battery, whether they are proponents of the battery hypothesis or critics of it, share a common commitment to understanding the artifact and the world that produced it. Their work, conducted in laboratories and in libraries and in the field, is a testament to the enduring power of human curiosity and to the belief that the past has something to teach us, if only we have the patience and the humility to listen. The artifact endures, the debate endures, the questions endure, and somewhere in the gap between what we can see and what we can know, between the physical evidence of a small clay jar and the interpretation that we seek to impose upon it, lies the answer to a question that has fascinated scholars and the public for nearly 90 years. The Baghdad Battery is not the only unsolved mystery in the history of ancient technology. It is one of many one thread in a larger tapestry of lost knowledge and lost capability that stretches across the ancient world. The Antikythera mechanism, the Lycurgus cup, Damascus steel, Greek fire, Roman concrete, and now the Baghdad Battery, each of these objects and each of these technologies challenges our assumptions about what the ancient world was capable of, and reminds us that the history of human ingenuity is longer, deeper, and more surprising than the standard narrative suggests. The clay jar from ancient Mesopotamia may be a battery, it may be a scroll container, it may be something else entirely. The answer matters, because the answer would tell us something important about the technological capabilities of the ancient world and about the nature of technological discovery. But the question matters too, because the question reminds us to look carefully, to think critically, to remain open to the possibility that the ancient world possessed capabilities that we have not yet imagined, and to treat the artifacts of the past with the respect and the attention that they deserve. The copper is green, the iron is rust, the clay is whole, and the question, like the jar that holds it, waits for an answer that may yet come. The artifact is small: a clay jar, a copper tube, an iron rod, a plug of asphalt. The materials are common, the construction is simple. The object, in its physical modesty, gives no outward sign of the extraordinary debate that it has provoked, or of the profound questions that it has raised. But the questions are not small. Is it possible that the ancient world discovered electricity? Is it possible that a technology that we consider to be a product of the modern era was anticipated, however imperfectly, by craftsmen who lived 2,000 years ago? Is it possible that the history of one of the most fundamental technologies of the modern world, the technology that powers our lights, our machines, our communications, and our civilization, has a chapter that was written in ancient Mesopotamia, and that was lost before the modern chapter began? The answers to these questions may never come, the evidence may remain forever ambiguous, the debate forever unresolved, but the questions themselves are a gift, a reminder that the past is not fully known, that the history of human ingenuity is longer and deeper than we sometimes imagine, and that the artifacts of the ancient world, however small and however modest, can still surprise us, challenge us, and remind us of the extraordinary potential of the human mind.